Yes, good afternoon, all of you. Yes, option C is correct. The answer for this question is option C, correct. Consider the following statement: the use of interpoles in DC machines. Why we use interpoles? To reduce the reactance voltage and also cross magnetizing effect of armature reaction in commutating zone. Commutating zone is nothing but interpolar zone, interpolar region. Okay, by using interpoles it is option C. Next question. Consider the following statements. Interpole windings are connected in series with armature winding. Right or wrong? Yes, interpole winding we connect in series with armature winding only. No, this statement is right. Polarity of interpole must be same as that of main pole in advance. Advance or ahead. Okay, this is right or wrong? First of all, observe which of the following statements regarding interpole used in motors. This is motor, not generator. If it is motor, what is the polarity of interpole? Behind. Polarity of interpole same as main pole, which is behind, not ahead. Okay, this is wrong. Generator or motor, you have to identify first. This is motor given. That's why ahead is wrong. Generator only ahead. Distortion of main flux under the pole shoes is not affected by the use of interpoles. Distortion of main flux under the pole shoes is not affected by the use of interpoles. Right or wrong? Yes, because whenever interpoles are placed, interpole flux and armature flux both will come at a time. That's why it doesn't affect the main flux. Distortion of main flux under pole shoes is not affected. That is right only. So 1 and 3 are correct. That is option C. Okay. Let's let us see now the characteristics of DC machines. Right, starting characteristics of DC machines. That is both generator and motor characteristics simultaneously we see here. Generator and motor. Generator and motor characteristics. First, we will see generator characteristics. See, in generator mainly we have three types of characteristics. Mainly, like there are some extra characteristics they are not required, just like whatever you have seen in the alternators. So in alternators, you will get load saturation characteristics and compounding characteristics. Compounding we draw between field current versus armature current. Here also same it is. And load saturation we draw between V versus IF for different load power factor. But here there is only one power factor. That's why it is not importance in DC generators like synchronous generators. Synchronous generators we draw this one also for different power factors. Variation of IF versus IA for lagging, leading, UPF. Similarly, V versus IF for different load power factor we draw. But DC generators we have only one power factor. That's why there is no importance of these characteristics in DC generators. Same as it is alternators it is. See, mainly in DC generators, we have three important characteristics. Similarly, in motor also we will see three important characteristics. They are first OCC, open circuit characteristics. Open circuit characteristics. Second, internal characteristics. Internal characteristics. Third, external characteristics. External characteristics. OCC. OCC is drawn between which two parameters? Always for every generator, not only DC, synchronous generator also, it is always EMF versus field current. That is open circuit characteristics. Voltage versus field current. EMF induced versus field current. Internal means in the armature inside, EMF is E, voltage is E, current in armature is IA, E versus IA. External means outside, that is terminal, that is voltage V versus load current V versus IL. Externally we are getting terminal voltage and load current. So this is V versus IL, we call external characteristics. Okay, so let's see. First, shunt generator characteristics, how we get. First one, shunt generator characteristics. Shunt generator. See, I'm not drawing for separately excited because separately excited and shunt generator characteristics both are same. So whatever we draw for shunt, almost same for separately. But there is a small variation. That variation I will show you here itself. Okay, both are same characteristics. Consider a shunt generator. See, this is open. Load is not connected. Then what is the actual OCC of this shunt generator? Already we have drawn this in the conditions to build voltage in self-excited generators, E versus IL. Already we have drawn the variation of this OCC. How? Even the field current is zero, still some EMF induced. That is due to residual flux, a small amount of EMF, let that is Eg1. Now when there is voltage here, when there is a voltage, a current will flow here, a small current like that. the voltage builds up continuously up to saturation of field poles. This is the open circuit characteristics, OCC it is. Okay, for all self-excited generators, OCC is this only, same. But we will consider this open circuit characteristics at a rated voltage. Suppose, just tell me, if you place a voltmeter here, place one voltmeter here, then you rotated at a speed n. Tell in how much time this voltmeter will show the rated voltage. So already we have seen what is the open circuit voltage of shunt generator, rated voltage, the 220 example. What is the open circuit voltage of series generator, residual flux voltage, small voltage only. After that voltage will not build for series, but for shunt generator, even there is open circuit or no load condition, there is a path for field current, ISH. That's why whenever field current is flowing, flux will increase, EMF also increases, voltage builds up. Now like that, in how much time this voltmeter will show you here rated voltage? Slowly it will build? No, immediately. Just if you start rotating at rated speed with prime mover or mechanical input, your voltage of this generator will reach a rated voltage, some 220 volts, for example, 220 volts within short time, like 2-3 seconds only, not more than that. But if you want to draw this OCC, what you have to do is step by step field current increasing. So there we will place one rheostat here in the labs. We will place one rheostat. That rheostat will decrease slowly. Like that, field current increases. Field current increase, flux increase, EMF increase. But in order to build this rated voltage, within short time, you will get rated voltage. Now, suppose after rotating at rated speed, just after 10 seconds, for example, after 10 seconds, what is the reading of the voltmeter? Rated. Now observe for 1 minute. What is the reading of voltmeter? Same only. Observe for 2 minutes. What is the reading of that voltmeter? Same only. So after that, voltage will not change. So voltage will come to rated and then fixed it is. After that, there is no increment in the voltage. It is always constant. That's why that constant voltage now I will represent here. Constant voltage. So I will draw that three characteristics in one graph paper only, like EMF, voltage, it is field current, armature current, load current. Field current also constant. Field current also will not change, fixed, and voltage also fixed. Now, if you draw the characteristics, this is no load condition, means load current is 0. At that time, what is the voltage of this generator? Rated. So this voltage or this dotted line we will consider as open circuit characteristics. Actual OCC is this is only step-by-step procedure, but this is the dotted line after the voltage become constant. So after that, voltage will not increase further. Same voltage the voltmeter will show you. That voltage I am representing as open circuit voltage. This is the open circuit voltage of shunt generator, some rated fixed voltage. Okay, this is E versus ISH, OCC. Okay, now internal characteristics we have to draw. Internal means we have to connect a load here. Connect a load. Now when load is varying, current supplied by generator also varies. Now there is IL and there is IA also. Now IA also increase. Now whenever IA increase, we need to draw second one, E versus IA. Whenever armature current increases, what happens in the armature? Armature flux increases. Whenever armature flux increase, reaction increases, effect of armature flux on main flux increases. Then what is the one of the effect in armature reaction? Demagnetizing effect. So due to the demagnetizing effect, some flux will reduce, which causes reduction in EMF of generator. Okay, so that is I am drawing here now. Whenever IA increase, armature reaction increase, more demagnetizing effect. That's why the EMF of the generator slightly decreases, slightly. Let us assume this no load voltage is 220 and this voltage will be approximately nearly that 217, 216 like that. Some 2-3 volts will drop, not more than that. Okay, this blue line indicates internal characteristics. Internal E versus IA it is. E versus IA. Consider this is the no load point. This is the full load point. Full load means what? Rated current. No load current means zero almost. Full load means rated current. So no load to full load we are considering. If load increases, current increases, EMF slightly decrease. More current, more reaction, more drop. That's why it is. Okay, slight decrease in the voltage. This is the variation of internal E versus IA. Now external characteristics. External is what? V versus IA. If you apply KVL here, what is the terminal voltage? EG minus IA into RA minus brush drop. So if you want the terminal voltage, this one, terminal voltage, from the EMF induced, you have to remove additionally that resistance drop and brush drop. So if you remove that, whenever load current increases, your terminal voltage also slightly decrease. Initially, this voltage drop is due to armature reaction. Now, again some voltage drops here. This voltage drop is due to mainly armature resistance drop. IA RA drop. When IL increase, IA also increase because IA equals to IL plus ISH only. If load current increases means IA also increase. Then internally drop increases, your terminal voltage decreases. Okay. So this is no load to full load, external characteristics. V versus IL it is. Clear? But totally no load to full load. No load is this, full load is this. How much voltage drops here? If it is 220, this is approximately some 215. Not more than that. 5 volts, 6 volts drop. Not more than that. Slight voltage drop. If you neglect that small voltage drops, you can treat shunt generator is a constant voltage source generator. Constant voltage source generator. Okay. Approximately it is a constant voltage source generator. Now, where we can use this type of generators, applications. Constant voltage source. Wherever you want DC voltage, there you can use. So previously we solved one question. What is that? Lighting loads. So we can use for lighting loads because lighting loads required a constant voltage. So shunt generator is suitable for lighting applications. Lighting. Wherever we require constant voltage. And we can use for battery chargings. Battery charging. And we can use for field winding. In alternator, particularly rotor field winding, DC supply required. So for that DC supply, you can use this. But right now, we are not using all this. So keep in mind, practically, if you get any question in interviews, these are just application. Practically, right now, where we are using DC generator means we are not using. Why? Why we are not using right now DC generators? The main reason is, yes, what is that? Advantage of our power electronics. That is drives available now. Drives converters available. Rectifiers, inverters, cycloconverters, choppers. So whatever you want, AC you want or DC you want, you can convert because what is available readily with us? AC. If you want DC voltage, convert with rectifier. Convert with rectifier, AC to DC, and controllable voltage. Whatever the voltage you want, you can give that. But if you use DC generator like shunt generator or any other generators, what is the constant maintenance of these generators compared to these static devices? Our generators is cost is more. That's why right now the applications of shunt generators practically so much reduces. So much reduced. We are not at all using DC generators now, practically anywhere. Now you people may get doubt. If we are not using, why we are learning? Yes, we have to learn because that is our syllabus. Whether we are using or not, that is our syllabus. We will get the questions from here. We have to answer and we should get a good rank. So for that reason, we should learn. That's it. And applications means these are the application we can use here. Okay, but don't say that right now we are using. And after that, motor characteristics we see. So there I will ask one question. So that is now itself I am asking. Where we use series generator? Where we use series generators? Tell me. Series generators. Where we use? See, guys, most of you given wrong answer only because you are not observing what I am asking. Where we use series generators? I asked. Okay, very good. Some of you given, very few of you given right answer, but most of you given a common answer that every electrical student will do that mistake. What is that? You are not observing what I am asking. What I am asking, where we use series generator, but I am not asking where we use series motor. Your answer is given for motors. That is most of you given traction or lifting application. Okay, right now understand? I am asking for generator, not for motors. Okay, if it is a series motor, traction is the answer. Even the application of series motor is traction, but right now in the traction, what is the motor we are using? Tell me right now. Practically, what is the motor we are using in traction? Is it series motor? No. Three-phase induction motors only we are using, not series motor. Yes, three-phase induction motor, squirrel cage, not slip ring. Squirrel cage induction motor only we are using. Okay, that's why theoretical learning is different, practically learning is different. So theoretically you are learning, that is you are knowing that this is we are using. But right now if you get any question in interviews, there we will fall down. Why? Because you will learn here. So series where traction motor means series motor. So don't learn like this. That's why when we learn, yes, right now practically we are using not that you should know again. These are all applications we can use. But right now in the traction, we are not using series motors. Induction motor only we are using. And if you get one question, which motor is having high starting torque? Series motor or induction motor? Yes, definitely series motor is the answer. Without using any controllers, which motor is having high starting torque? Series motor or induction motor? Answer is series motor only. But nowadays there is a technology, drives available for us. When there is a drive available to the same induction motor, you can increase the starting torque, you can increase the speed to very high values with the drives technology. So using this drive, you can generate the torque of induction motor very much greater than series motor also. How? Tell me any idea if you have. How can we increase the starting torque of induction motor? Tell me. How can we increase the starting torque of induction motor? By increasing resistance. See, you can increase the resistance for slip ring induction motor, but not squirrel cage. I said squirrel cage induction motor we are using. How can we increase? Yes, by changing frequency. And what we have to change the frequency? Reducing or increasing? Tell me that. Reducing or increasing the frequency will increase starting torque. Which one? Reducing the frequency or increasing the frequency? Hmm. So did you remember that relation? What is the starting torque and frequency relation? Starting torque and frequency relation in induction motor. Inversely proportional. And how much it is? How much? Okay, enough. So I will tell. Just listen. In induction motor, we have one relation. Starting torque is proportional to 1 by F cube, cubic frequency. If you want high starting torque, little reduce the frequency. Little reduce the frequency. If you reduce a little, your starting torque increases by so much. Using this technology, we are operating traction motors right now, induction motors. And that motors are squirrel cage, but not slip ring. Maybe you are thinking that slip ring is having high starting torque, that's why it is suitable. See, squirrel cage having low starting torque, but we can increase the starting torque using this technique. And squirrel cage induction motor is less maintenance, less cost compared to slip ring induction motor. In slip ring induction motor, there is slip rings and brushes. When there is brush and slip ring combination, maintenance increase because brush is not the permanent body. It is a temporary body. Whenever motor is operating, brush gets wear and tear. So you need to replace new brushes, new slip rings. So these are all maintenance. But squirrel cage induction motor, once you buy, you can forget about the motor. That is the life of motor. Why? Because in the squirrel cage induction motor, the rotor winding is copper bars, and all copper bars are short circuited. Due to that, as it is heavy copper bars, rotor winding never burn because heavy copper bars, whatever the high currents are flowing, it never damages. But slip ring induction motor, there is a winding, thin wires, that winding may damage. But squirrel cage rotor winding is the strongest winding, it never damage because thick wire it is. If anything damage in the rotor, the end rings only will damage. Copper bars will never damage. End rings. Sometimes, due to the centrifugal forces, the end ring may come outside or end ring may come out of the copper bar. It may open. Then it is open circuited. Then motor cannot rotate. At that time, end ring we have to attach properly. That is only the thing will damage in the rotor, and nothing will damage in slip ring induction motor, squirrel cage induction motor. Okay, like that, theoretical is different, practically we are applying is different. Both you should know. Yes. Okay. So we can use this shunt generator for lighting application, battery charging, or power supplies. Auxiliary power supply we call auxiliary power supply, or as exciter for field windings, exciter for field windings to create flux, etc. etc. Wherever you need constant voltage, you can use shunt generator there. Now here important is so here important is what is the nature of this shunt generator characteristics. Nature means how they are behaving from no load condition to full load condition. What is the nature of these characteristics? Voltages slightly decreases. This nature of characteristics we call drooping characteristics. Droop is nothing but slight drop in any value we call droop. Here voltage also slightly decreases. If it is 220, it is 215, like 5 volts, 6 volts drop. That is called drooping characteristics. Okay, so right here, the nature of shunt generator characteristics from no load to full load, from no load to full load. The voltage of shunt generator, the voltage of shunt generator slightly decreases. Slightly decreases. Hence, approximately, it is treated as a constant voltage source generator. A constant voltage source generator. Okay. The nature of characteristics is called the nature of characteristics is called, this is also important for objective questions, drooping characteristics. Drooping characteristics. The nature of characteristics is called drooping characteristics. Droop is slight decrease. application of series generator, we will see this. Okay, in the boosters we use, in the transmission lines we use series generators. Now, generally we operate every generator, every motor, no load to full load. Okay, no load to full load. In your lab also, while conducting brake test, you will apply brake on the motors belt. Up to what you will apply brake on the motor? Can you apply whatever you want tightly? No. We will apply the brake in the lab by observing ammeters. We will connect one ammeter, how much current motor is drawing, we will measure. And we know already from the nameplate, the rated current of the motor, suppose 20 amps. That is the full load current. So we will apply the brake on motor up to motor is drawing 20 amps only. More than that, we should not apply. Okay. So like that, every generators and every motors, we operate always from no load to full load condition. Safe operation it is. Otherwise, if you apply whatever the load on that, it may overload and the motors or generators may damage. That's why this is no load to full load operation. Now we will go to abnormal operation. Suppose now I will keep on increase the load on generator. The load I am increasing continuously. Then what happens to these characteristics? Is the generator will damage or not? We have to check. Suppose load I am increasing continuously. Load means what in your lab? Resistors. Resistor banks will be there. 1 amps, 2 amps, like that. If you keep on increase the load, 1 amp, 2 amp, 3 amp, 10 amps, 15 amps, 20 amps, and so on continuously, the current becomes finally short circuit, very, very, very high. Then generator will damage or not? Tell me. If load on generator continuously increases, then generator will damage or not? Definitely it has to damage, but there is one important property of shunt generator, that is it is a self-protected generator. It never damage. If you apply voltage or load on this generator continuously, automatically it is self-protected. Automatically it is protected. It won't damage. Okay, see how it is. And if you apply the same load on separately excited generator, that separately excited generator definitely will burn. So I will show you both cases. Observe now. Make a note of this. Note. Suppose this is the characteristics we got. No load to full load. Let EMF, voltage, load current or armature current. This is the no load characteristics or open circuit characteristics up to here. And EMF of generator, internal. The internal characteristics are slightly decreased up to here. No load to full load it is. And external is this one. Little drop again. External voltage. This is internal voltage. This is external voltage. So whatever we have seen just now, same it is. Now observe what happens. Suppose you are applying continuously load on this generator. Generator should damage, but it won't damage. That is the advantage of the shunt generator. See. Now, load increase. Load increases. Current increase. Load increase, nothing but current increase. How current increase? Generally, if it is a shunt generator, how we connect load to the generators? Parallelly. We connect load parallelly. Let us, for example, initially one resistor is connected. One resistor. Now again resistor is connected. Load is added. Again load is added. Like that continuously we are adding load on this. Then what is the equivalent resistance of this? Assume that same resistors, 1 ohm, 1 ohm, 1 ohm, I am adding continuously. Like that hundreds of resistor add. Then what is equivalent of this load resistance? Equivalent. If there are two resistors, what is equivalent? Half. If two resistors are in parallel, equivalent how much? Half only. If three resistors are in parallel, R by 3. 4 in parallel, R by 4. Like that, if there are infinite in parallel, what is the equivalent resistance? 0. 1 by infinite. Means what is the load resistance? 0 means it is a short circuit or not? Yes. So for example, I am increasing the load on the generator continuously. Now what happens here? Observe. See, whenever load increase, up to full load it is. Up to here only we have to apply load. More than that we should not apply. But still I'm applying still load on this. Load applied. What happens is, whatever this EMF is there, first I will take terminal voltage. See, terminal voltage decreases because load increases further. Terminal voltage decrease. At one of the point, this voltage come back to zero. This voltage come back to zero. It is. This is called reversal of characteristics. Reversal. Characteristics will come reverse. Why it is reverse? Why it is reverse? Tell any idea if you have. If load increasing like this continuously up to infinite, after a particular value of current, the voltage of this generator reverse. Decreases, and current also decreases. Current from this point, current also decreases. Decrease. And this is the current. Actually, under short circuit, what should be the current? Very, very high. But current here is not very high. It is limited. It is limited current. Even under short circuit. Short circuit means what is the voltage across the short circuit? 0. See, this is a short circuit. What is voltage here? 0 only, no? That's why voltage becomes 0. This is voltage axis. Voltage curve it is. Voltage becomes 0. Voltage becomes 0. But there is a current here. This is current axis. There is some current here. This current is not 0. A small amount of current is flowing. Actually, under short circuit, high current has to flow. But it is not flowing. It is flowing very small current, less than full load almost, less than full load. How it becomes like this? Tell me. How it becomes like this? See, from the shunt generator, what is the armature current equation actually? Eg minus V by Ra. Eg minus V by Ra. And what is the load current? V by RL. Load current means, observe the figure. This is load current, IL. What is load current? Voltage across the load by load resistance will give load current. How to find IA? Eg minus V by Ra. Okay, Eg minus V by Ra. Now, this is the equations, IA and IL. Whenever load resistance load increasing means resistance decreasing. Don't confuse. Load increasing means resistance decrease. That is only, no. Load increasing means resistors I am adding. What is equivalent resistance? Finally 0 means it is decreasing step by step, and finally 0 it is. So load resistance decreasing means current increasing. Whenever current increase, what is IA also increase? Whenever IA increase, what is IARA drop? Increase. When IARA drop increase, what is the terminal voltage? Decrease. Whenever voltage decrease, what is the field current of the generator? Decrease. Because in shunt generator, ISH equals to V by RSH. ISH equals to V by RSH. Okay. Whenever voltage is decreasing, ISH also decrease. When ISH decrease, what is the flux in generator? Also decrease. If flux decrease, what is EMF induced in generator? That is also decrease. That's why your armature current decreases. Your armature current decreases. Okay. It won't increase. It will increase up to a particular value. After that, as voltage drops, field current also drops, flux in generator drops. So during that, EMF decreases. That's why it is come back. Voltage decrease from this, and the same time current also decrease, because when voltage decrease, that is EMF is decreasing inside the generator, so current also decreases. Finally, as load is infinite resistors are connected, then what is the voltage? 0. Short circuit, no, it is infinite resistance means 0 resistance, short circuited. Always at short circuit condition, voltage is 0. That voltage is 0. Now, how that internal EMF will behave? Here also the same. Whenever load increase, EMF decrease. After a particular point, it is also reversal. But this EMF will not become zero. It will be a small amount of EMF that is not zero even under short circuit. Even under short circuited, this EMF of generator will not become zero. A small value will be there. And how much value it is? Why this is present? Whenever voltage zero, so little concentration required. So don't sleep in this time, because generally afternoon time is definitely after eating, definitely sleep will come. But we have to bear. Okay, don't sleep. Getting sleep, because I cannot make any entertainment. So all of you listening? Okay, good. Okay, very good. Okay, enough. Good response. See, when load is infinite, means resistance zero, voltage short circuit. Whenever voltage zero, what is the field current totally? Zero, because ISH equal to V by RSH. Now total field current zero. Then what is the total flux in the generator? Is it zero? No. This is only residual flux. Even current zero in the winding, there is total flux will not become zero. There is a small amount of residual flux. Due to that, there will be a small amount of EMF, that is EG, which is some 5 volts, 6 volts, 7 volts, small voltage. Due to that, a small current will be there or not. IA equal to EG minus V, that V zero. But even that is zero, there is a small EMF. That's why small current is there. That current is this much. The value of current at this point is IA equals to EG by RA. That's why that small current is there, because small voltage is there. EMF is not zero. Okay. So this is the behavior of shunt generator characteristics. Now observe, even short circuited, what is the current of this generator? Small current, limited current, not very high current. That is called self-protected generator it is. Now if you take separately excited generator, for example, it will damage. Separately excited generator will damage. Separately excited generator. Field current constant here. It won't change. Field current will never change, because separate DC voltage source to this, flux is constant. When flux is constant, if you rotate at a constant speed, what is EMF of generator? Always constant. Now let us add load here. First one resistor added. One resistor connected. Like that, keep on adding load. Keep on adding load. Means infinite resistors added. Then what is the equivalent road resistance? Zero. Zero resistance means short circuit. At short circuit, what is the voltage? Zero. Then what is the current here? IA equal to ISC, which is very, very, very high. Your armature will burn. Why? What is IA now? EG by EG minus V here also. But V is what? Zero divided by RA. This current is very, very high. Why very high? EMF is not a small voltage. EMF is rated voltage. That is whatever induced previous, because flux constant, speed constant. Same amount of EMF is there. But in shunt generator, what happened? In shunt generator, whenever load increasing, terminal voltage decreases. Because of that, field current also decrease simultaneously, flux also decrease, EMF in generator also decrease. EMF is not same here. That's why current is limited in this. Okay, clear all of you this point now? Okay. In series motor, we will see first generators we have to complete. Then we go to motors. Okay, right here in the note only. So this is all in note. Make a note of all this. Below this figure, write some points. Below this figure, write some points. First complete this figure. Series generator after this. We will see series generator after this. Voltage graph only this shape is we are getting like that. That's why we are drawing. Any other shape is how we get voltage decrease, decrease, decrease. After a particular point, voltage decreasing. After a particular point, what happened? Voltage decreasing. So field current suddenly drops. No, field current also decreasing. Flux decrease. Then voltage decrease. And voltage decreasing, current also decreasing. That's why we get this shape. So why not other graph means? How can we say this? Okay. Clear now? For series generator, we will see after completion of this. So right below this figure. Right. Whenever the load on shunt generator increases, whenever the load on shunt generator increases continuously, increases continuously up to infinite load, up to infinite load, then the voltage, then the terminal voltage of this generator, terminal voltage of this generator also reduces to zero during this the field current and flux in generator also reduces. Flux in generator also reduce, comma, which reduces the EMF of generator. EMF of generator. Full stop. Therefore, hence, the shunt generator is a self-protected generator. Is a self-protected because even if you apply infinite load, current is not high current. It is a low current only. But it is unable to supply that load. See, load increases, current decreases. Current decreases means that loads cannot operate properly. That's why on shunt generators, we should never apply overloads. If you apply overload, its voltage drops to so much low value. So low voltage means not suitable. So low voltage should not be there. No, if low voltage is coming, the loads cannot operate. Suppose you take lighting load itself. Whenever voltage is low, your brightness of the light will decrease. Then that is not the desired condition. That's why we should not apply more load on this. The shunt generator is a self-protected generator with limited armature current. But what happens in case of separately excited? If load is keep on increasing, armature current also continuously increase. Definitely because of the high currents, armature winding may damage, but not happening in case of shunt generators. Okay. Right. Second, the series generator characteristics. Next, series generator characteristics. So this is the point at short circuit condition. This is at short circuit. At short circuit, voltage zero, terminal voltage zero, but current is limited because EMF also very small at that time. EMF induced also very small. That is due to residual flux only. So without nameplate, you cannot identify. See why this E and V are not decreasing like this means. See, whenever voltage decreasing, that's why I said when voltage decrease, field current decrease. When field current decrease, what is flux decrease? When flux decrease, what is EMF also decrease? When EMF decrease, what is the overall armature current also decreasing? Decreasing means after some this value, current decreases. Current decrease means this is the current axis. If you draw in the same way this voltage, is it current decreasing? Not, current increasing further. That's why it should not come like this. It will go in this way. That is only current decreases. Okay, clear now? Why we are drawing like this? Next, series generator characteristics. So this is most important in interviews. Series generator characteristics many times faced by so many students. Series generator characteristics. Why? Because many times the common question I heard is draw the series generator characteristics. OCC, draw the open circuit characteristics of a series generator. Okay, how to draw that? So maybe you know OCC of series generator, rising characteristics we call rising. So generally we give this is in class, but if we don't say this point at the interview stage, the people are drawing same graph again, OCC of series generator. Now, that is a wrong indication. You should not draw directly like this. Okay, OCC of series generator is not possible first. OCC of series generator is not possible directly. If you want to draw OCC, you have to operate the series generator as a separately excited generator. Remember this point. See, consider a series generator first. Consider a series generator. Now, if it is open circuit, suppose open circuit it is, load is not connected. Now, place one voltmeter also across the armature. Now, tell me, under open circuit, what is the voltage induced in series generator? How much voltage induces? Only a small voltage, that is due to residual flux. So more than that voltage will not come. More than that voltage will not come. Then how can you draw OCC? If you draw OCC means voltage versus EMF versus field current. In case of series generator, armature current, field current, load current, all are same only. See, if it is open, there is no path for current. Then if you start rotating at a speed n, how much this voltmeter will show? A small voltage, let 5 volts. That voltage is due to residual flux. And after that, you don't have any voltage. Then how can you draw OCC? OCC not possible for series. It is not possible. So if you want to draw OCC for series, how to draw OCC is remove the field winding from armature. Now give a small DC supply to the field winding separately. Small DC supply, not rated voltages again. Small DC voltage. Why small DC voltage? Why small DC voltage? Because what is the resistance of the series field winding? Low resistance. Thick wire it is, low resistance. As it is very low resistance, you should not apply very high voltage. Then if you apply high voltage, field winding may burn again. That's why small DC is required here. Now let us increase this voltage step by step by calculating or measuring this current step by step. 1 amps, 2 amps, 3 amps, 4 amps. Like that, if you give supply, current will flow. Now flux in generator increases. Now you are rotating at same speed. Now your voltage rating also increases. So like that, you try to draw the OCC. See, field current 1 ampere and 2 amperes, 3 amperes, 4 amperes, 5 ampere, 6, like that, whatever rated current. Like that, if you increase the field current, your voltage of series generator also increase, and due to saturation of poles after a particular field current, it will be constant. This is the OCC of series generator. So whenever you face this question, you have to say the first point, OCC for series generator directly not possible. So in order to draw OCC, we need to operate the series generator as a separately excited generator with low voltage source connected to the field winding. This is only the procedure for OCC. Okay, field current increase, flux increase, EMF in generator also increase. This is OCC procedure. Next, remaining internal, external. The two we have to draw, internal characteristics and external characteristics. How to draw? Again, remove from external voltage source, reconnect this with the field winding and connect a load here. Now connect a load. Now vary the load step by step. Vary the load step by step, like IL equals to 1 ampere, after that 2 ampere, after that 3 ampere, and so on up to rated current, whatever it is, up to that. Increase the load step by step. If load increase, flux also increase, EMF also increase. Now there is a armature current. Because of the same armature current, reaction takes place inside. Some voltage will drop. So if you draw OCC, internal is very easy. Just draw below that. Draw below this. This is the internal characteristics. E versus IA. Why some voltage drop here? This voltage drop is due to armature reaction drop. Armature reaction, when IA increase, reaction increase, demagnetizing, your EMF little drops. That's why voltage reduces. This is internal, E versus IA. Now what is external? If you want the terminal voltage from KVL equation, EG minus IA into RA plus RSC drops, plus minus brush drop. This is V, terminal voltage. Now terminal voltage less than this EMF. That's why terminal voltage is less than that. Again voltage drops here. This voltage drop due to resistance drop, IA into RA plus RSC main. Okay, external characteristics, V versus IA. Clear? See, for series generator, every time the no load, from the no load, this is the no load point. Or no load means open circuit. Assume that full load it is. This is full load. No load to full load. What is the voltage of series generator? Continuously rises. That's why the nature of characteristics of series generator we call, tell what is the name of this? Rising characteristics. The nature of series generator characteristics we call rising. It is increases. If load increase, current increase, flux increase, EMF also increase, or voltage also increases. Like that, it will rise continuously. No load to full load condition. But what is a shunt generator? No load to full load, the voltage of shunt slightly decrease. That's why that is drooping, but it is rising characteristics. Now, what is the voltage of series generator? Variable or not? Yes. No load voltage is 5 volts. Full load voltage is let 220 volts. So how much variation from no load to full load? So much variation. That's why The series generator we treat as a variable voltage source generator. It is a variable voltage source generator. But shunt generator is constant voltage source generator. But it is variable voltage source. First complete the figure. Okay, good. See, uh, so I will tell. Some of you asking, how can we connect field winding? How can we disconnect field winding from armature? This one. How can we disconnect? How can we disconnect it? Suppose there is a machine in series generator in front of you. Can you disconnect that? No, you cannot disconnect. But in the labs only it is possible. Labs in your colleges. In the labs, you have the boards, panel boards. So the field winding, they will indicate separately F, F, F terminals, A terminals. Now, if you join whites only, they are connected inside. Okay, then only you can open. That means, but if it is directly a series generator in front of you, you cannot open. You cannot remove that field winding outside. No, first, this is possible only in labs, lab experiments, but not directly. Okay. See, to draw the OCC of a series generator, what is the procedure? We have to remove the field winding from armature. Field winding from armature, and it is connected to a separate voltage source, a small voltage source. Now let us increase this voltage step by step. Variable voltage it is. When voltage increase, what is the current in the field winding increase? If current in field winding increase, what is the flux increase? If flux increases, what is EMF in generator? It is rotating. Then what is EMF of generator? Also increase. So that is we have drawn for different values of field currents. EMF induced. This is the OCC of series generator. For different values of field currents, we have drawn this voltage. So voltmeter is there, field current ammeter is there. So you can draw voltage versus field current. After that, internal, external. How we draw internal, external? To draw internal and external, you have to reconnect field winding to armature and connect it to a load here. Load. Now increase the load step by step. Whenever load increase, current increase, flux increase, EMF also increase. That is we have drawn internal characteristics. By why, but why it is less than the previous? Yes, reduce. Why reduce? Due to armature reaction drop will be there inside. But previously in OCC there is no reaction. Previously while drawing OCC there is no reaction. Why? Armature we open na here. This is open. This is open. No current in armature. Only field winding there is a current. Okay, got it all of you now? Initial voltage is due to residual flux. That is already we know, no? Yes, armature reaction only in loaded case. That's why some voltage drops. Terminal voltage again reduced due to resistance drop. Okay. Okay. So we write some important points. See, please don't sleep anybody, because if you sleep maybe after 1 or 2 minutes, when you see you cannot understand, then you may ask, because I cannot repeat so many times. Please don't sleep anybody. See, in offline class we observe who are sleeping, who are listening, we can understand. But here we cannot observe anything. Completely your responsibility. So your support is very important in online class. Okay, very good. नींद पीक पर है, कुछ चाय पी के आ जा। क्या नाम तेरा? नाम नहीं बताते कुछ लोग। Yes, when armature winding and field winding are disconnected, then only we are drawing OCC. That is only enough because armature inside that is rotating. How we are producing flux? Like a separately excited generator. Just you assume it is a separately excited generator. However, there is voltage here also same. Okay. Okay, very good. And some of you very fast, like okay. So I will come to that point. Just wait for some time. Okay. Speed control mostly today only will start. After completion of generator and motor characteristics, we go to that. So here it is non-linear only because series generator nature is that is we cannot do anything. So that is a non-linear characteristics. Okay. 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 Enough. Now right here some important points. Right. The OCC of series generator. The OCC of series generator can be draw by it operating it as a separately excited generator. By operating it as a separately excited generator. Okay. OCC we can draw by operating it as a separately excited generator. That's it. Next, to draw internal and external characteristics. External characteristics. Connect a load which is variable. So we have to vary the load here. Suppose if you connect a load and fixed one, then voltage will not rise. At a particular load, one voltage only will be there. Suppose you connected a load of 10 amperes. 10 amps means flux will generate accordingly, EMF also will generate accordingly and fixed. After that, no variation. That's why whatever the load we connect, which is variable, that is important. Variable load you have to connect and vary it from low value to rated value, no load to full load. Okay. The voltage of this generator, from no load to full load is rising continuously. Hence, it is called as a variable voltage source generator. A variable voltage source generator. Variable voltage source generator. The nature of characteristics is called rising characteristics. Rising characteristics. Okay. What are the applications of series generator? Where we can use this? So there is one important application of series generator, that is we can use this series generator at the boosters as a booster in DC transmission lines. Application of series generator. It is suitable as a booster. It is suitable as a booster in DC transmission lines. DC transmission lines to compensate voltage drop. To compensate voltage drop in the lines. Voltage drop in the lines. So generally some voltage will drop in every transmission line, whether it is DC or AC. Now in AC transmission system, what is the booster? Which one we use booster? So already we have seen in transformer. What is booster there? Auto transformer. Okay. Auto transformer is a booster in AC transmission system, but in DC transmission, DC series generator is suitable as booster. Why we call booster? It will boost the voltage or increase the voltage or compensate the voltage. How it will compensate is, for example, this is a transmission line, DC, sending end voltage, it is receiving end voltage, receiving end. So assume that this transmission line length is approximately some 100 kilometers, so much distance. Now, because of that long distance, if sending end voltage is, for example, 200, what is the receiving end voltage? Do you get the same voltage here? No, definitely some voltage will drop. If you connect a load, definitely some voltage will drop. What is the receiving end voltage? You will get less than that, let 190 volts. Some voltage will drop in the lines, in the transmission lines. Okay. Now, whatever drop is there, that we need to compensate by connecting a series generator here. Series generator is connected in series with this one of the line. Now, what happened? What happens? See, if it is 190 receiving end, if it is 200, a current is flowing through the transmission line or not? Yes, a small current is flowing. 200 minus 190 by impedance or resistance of this line, because DC resistance. Then a current is there. Due to that current, same current will go in the series generator, field winding also, flux proportional to same current. Whatever the amount of current is flowing, that much amount of flux will generate. Whatever the flux is generated, that much EMF will induces here. Now, whatever EMF is induced, that is compensated. Whatever 10 volts is dropped, it will induce approximately 10 volts. Now, what is that voltage here? 190 plus 10, 200. Like that, voltage compensating. Whatever drop is there, that will compensate. No other generator suitable as booster. Because can you connect shunt generator in single line here? Not possible. Only series, only one winding generator is suitable. Like that in AC case also, what is suitable for one line? Auto transformer, because that is having single winding. But two winding transformer you cannot connect. Single winding transformer only you can connect there. That's why auto transformer having single winding, that is suitable in AC transmission. And DC transmission, this one, DC series generator. It will compensate voltage drops. Okay. Now let's see here also what happens if load increases continuously. Just like shunt generator, what happens here? If load increases on series generator continuously, what happens? Let's see that. So in motors, bike engines, we don't use these motors. Bike engine, they are IC engines, no? Internal combustion. So that is mechanical students knows very well. But it won't come under electrical motors. See what happens in series generator if load increases continuously. Observe it is. For example, series generator, load on series generator continuously increase. What happens in this? Observe. Actually, no load to full load. This is internal characteristics. This is internal. I'm not drawing OCC. Internal I'm drawing directly. Internal EMF E and external characteristics below this. Little voltage drops. This is external voltage characteristics. Internal and external. Now this is our no load point, and it is our assumed full load point. Up to here only we have to apply load on the generator. Safe it is because current is rated full load condition. Suppose by mistake you applied beyond this point load on the series generator continuously. What happens now? Tell me. If load increases continuously, what happens? Is current increase or voltage increase or what happened? See, if load increases from now, load increase means current increase. Then what is the voltage V? See, load increases means what is the terminal voltage here? Decreases, because whenever load increase, IA increase, drop increase, your voltage will decrease. So voltage decreases. This is a saturation point here. Saturation voltage is there. This much voltage. Full up to full load, no problem. This much voltage is there. But from now, if your load increase, now your voltage starts decreasing from this point. Voltage decreases. Why voltage decreasing? Drop, more drop, because already flux is constant. Your EMF will not increase further. EMF proportional to flux. As current increases up to full load, flux is almost maximum. Saturation takes place. Now flux is constant. Flux will not increase further. That's why EMF is almost assumed constant. But voltage is what now? Decreasing. Voltage decrease, decrease. Voltage decrease. Still load increases, voltage decrease, decrease. At one of the point, this voltage will reach to 0. Now, whenever voltage is reaches to 0, what is the magnitude of EMF at that time? See, IA equals to what? IA. The IA equals to, from this KVL equation, IA equals to EG equals to V plus IA into RA plus RSA. This is the KVL of series generator. From this, what is IA? That is, I'm writing IA equals to EG minus V divided by RA plus RSA. Okay. Load increases, finally voltage 0. Now, when your voltage 0, what is the current? EG by RA plus RSA. RA plus RSA. Now, what about this EMF? What about that EMF? Is it remains same or it will also decrease? Tell me. Is it same or it will also decrease? Answer. The EMF remains same or EMF also decreases? Okay. Yes, very good. The answer is decreases due to armature reaction. Main flux is constant, but whenever IA is increasing, na here IA it is IA increasing. What is armature flux? Increases continuously. When armature flux increase, what is the reaction? Increase. More reaction. If reaction increases, demagnetizing. But because of demagnetizing, your EMF also decrease. But it won't decrease up to 0 value. It will decrease up to here. Whenever voltage 0 at this current, this much EMF is there. This EMF is not 0. This EMF is due to what? Due to some current. What is that current? This much. When there is IA of this much, flux proportional to same armature current. Okay, based on that, some flux is there. It is not residual flux. There is some high flux only. So this much EMF will be there. and that armature current is Ia equals to Eg by Ra plus Rse. This current is little high current only. High current it is. This is full load current. This is high current. This is high current, not low current. Now this high current may damage armature winding of series. That's why we should not apply load on series generators by mistake also very high. It is not self-protected. Only shunt generator is self-protected generator, but it will damage. Okay, so this is the variation of characteristics of series generator in overloaded condition. Overloaded condition. Clear now? So this is under overloaded operation of shunt and series generator. Shunt generator is self-protected, no problem to it. But series generator definitely damaged because high current will be there in this. High current. And under short circuit condition, voltage 0, at that time the armature current is Ia equals to Eg by Ra plus Rs. This current is high current, so flux also high. The EMF in that also little higher only. Main field will not reduce, but main field is reducing. But there is some current now. Because of that, main flux is not low value, high value only. Main flux is little higher value only because there is a current. Flux in series generator, main flux also proportional to armature current. If current is not zero, flux also will not become zero. There is some current here. See, this much current is there. This is high current only, not low current, because armature resistance and field resistance is a small value, less than 1 ohm. That's why current is higher. High current, high flux, high voltage is there. This much EMF is there. But in shunt generator, EMF is very, very small, residual voltage. That's why current is limited there. No, arc welding we don't use. Arc welding we use differential compound. Okay, right. So this is about series generator characteristics. Now let's see compound generator characteristics. Right, next one, compound generator characteristics. Compound generator. Let us consider a compound generator. Anyone we can take. Suppose I'm taking a short shunt compound generator. See this. First tell me, under open circuit condition, what is the voltage of compound generator? Whether it is cumulative or differential, anything. What is the voltage? This is open circuit now. Generator is open circuit. Now, what is the voltage induced in compound generator? Tell me, is it a 0 or small voltage or rated voltage? 0, small voltage, rated voltage. What is the answer? Yes, rated voltage. Rated voltage it is. It is a rated voltage because even it is open, there is no current here. Current in this is 0, but there is a current through this shunt field or not? Yes. Now it is similar to shunt generator or not? Yes. Under no load condition, a compound generator is almost similar to shunt generator. Shunt generator only it is. Just like shunt generator it is. Okay. It is a shunt generator. Got it? Now what is voltage induced in that? Rated voltage. Let under no load condition, little concentration required to understand this, because previously I said over compound, flat compound, under compound. That compounding we get by adjusting series field. That we will observe how we will get over compound more voltage, flat compound almost same voltage, under compound low voltage. How we will get with some examples I will give you. Try to concentrate. Don't sleep again. Okay. Actually, in offline class, I never ask anybody don't sleep. But here asking because if you sleep after some time, you will message how it is, why it is, where it is. That's why. But in offline, no. If he is sleeping, I know who is sleeping. Then if he is asked, he cannot ask also because he knows that I observed. Okay. Till 5 p.m. No, not possible at a time. So break we take at 4 o'clock. No break. After completion of generator characteristics, we take break. Yes, offline also started. Okay. Don't sleep. Concentrate. Main flux proportional to main flux. Very good. Good observation. Back pain. IA is proportional to, see, main flux proportional here, series machine, main flux, armature flux, both proportional to armature current only. Okay. Both are proportional to armature current. Okay. Listen here. See, this is no load condition. Open circuit now. Under no load. So I am considering example, the EMF induced in the generator E equals to no load voltage it is. This is equals to, I am taking let 200 volts. Let 220 I am taking. 220 volts. The EMF induced in the generator is 220 volts. Let example taking 200, better understanding. Let the EMF induced under no load condition is 200 volts. This is called no load voltage. This is no load voltage. Whether it is cumulative compound or differential compound, no load voltage is same for both. Okay, this is no load voltage for both cumulative and differential. Okay, in cumulative we have three types: over compound, flat compound, under compound. So that three characteristics we have to draw here. First, we will draw that over compound, flat compound, under compound. Then we go to differential compound generator. And moreover, we are not drawing now the three characteristics in this. That is OCC, internal, external. We don't draw here. We will draw only external characteristics. Okay. So no need to draw again OCC internal. Just like it is similar to shunt generator or series generator. So if you know external characteristics, what is the OCC? You can draw above that. Or internal also. Internal is above external. OCC is above internal. So that you can draw remain. But only external characteristics I'm drawing here for all generators in one graph. Okay. As there are many combinations again in compound, we cannot draw all OCC internal, external. Only external characteristics are there for the compound generators. See, this is external means V versus IL. External means V versus IL. This is the no load condition. No load current. No load. Okay, at no load, what is EMF induced? 200. This is the no load voltage. 200 volts. This is the no load voltage. Let it is the full load point. This is full load point. Okay. No load current, it is full load current. This is no load voltage. No load voltage. Now, so I'm taking the first one is over compound generator. So in order to get compound generators, three types: over compound, flat compound, under compound, we have to adjust the series field winding in this. That's why I am placing one diverter here. Observe this. I am placing one diverter across the series field winding. Diverter. This is called diverting resistance. And this is the field resistance of field winding, RSC. Armature resistance, shunt resistance. Okay. Now first I will take over compound generator. Over compound generator. So if you want over compound generator, over compound means series MMF is greater, higher. So let us create a series flux is higher value. Flat compound means reduce the series flux, suppose almost equal to shunt flux. And under compound means series flux is less than shunt flux. So here in all these three generators, over compound, flat compound, under compound, you need to adjust series flux. How to adjust series flux? Series flux proportional to the current through this, that is ISC now. And this current is called diverted current ID. See, without a diverter, what is the current in the series field winding? IL only. Same load current will flow in this if load is connected. If load is connected, current will flow through this. Okay. Now, whenever diverter is connected, some current is diverted in the diverting resistance and some current will flow in the field winding only. That is the current ISC I taken. So series flux depends on the current ISC. Okay, remember this. Now, for over compound generator, I need more series flux. For over compound generator, I need more series flux. For that reason, what should be the series field current? Higher value. If you want series field current higher value, what should be the diverting resistance? Tell me. What should be the diverting resistance? High value or low value? Diverting resistance should be high value. So under full load, no load voltage is this 200. Same I taken 200. No load voltage is 200 only. Now under full load, what I will do is I will adjust the diverting resistance such that very high value it is. I will, that is a rheostat. I will keep higher value of diverting resistance. If RD is higher, what is the current ISC? ISC is increases or not? If I keep high value in RD, ISC will increase or not? Yes. Why? Observe this. If this resistance is higher, what is the current ID? Less. Then out of the total load current, most of the current will come in field winding only through this. Current in field winding increases. Okay, understand. For over compound, I need higher value of RD here so that field current will increase. Current in the field winding increases. So ISC increases. Whenever ISC increase, what is the total flux in generator now? Cumulative. These three are cumulative only. So as it is cumulative, total flux is sum of the two fields, phi sh plus phi sh. Previously with only no load voltage, what is the flux in generator? Only phi sh. No series flux at that time. No series flux because it is open na previously, zero current, no flux in that. So at that time, no load, the flux is only shunt flux. But now when load is connected, full load condition, we have adjusted RD like this. Then the total flux in generator is phi sh plus phi sh. Now as total flux in generator increases, what is EMF of generator? Also increases. Increases or not? Yes. Now let us take the EMF induced is 240 volts. If EMF induced is 240, what is the full load voltage? Voltage across load how much? Less than that. So let us considering this is 230 volts. Voltage less than that EMF induced. This is called full load voltage. This is called full load voltage. No load voltage means this one, 200. No load voltage is this one, 200. Full load voltage is 230 volts. Okay, by proper adjusting of this RD, we got this much voltage, full load voltage. Now, if you draw the characteristics, no load voltage 200, full load voltage 230. How we get characteristics? No load is 200, this much. Full load is 230. That's why your voltage will increase. At the full load, what is the voltage? 230 volts. No load 200 volts, full load 230 volts. This is the characteristics for over compound generator we get. Okay. Now let us take flat compound. You will understand after completion of flat compound what we are doing here. See this. Second, I am taking flat compound. Flat compound. Don't saturate. So much is there still to learn. Don't saturate. Don't sleep. Now flat compound generator. Even for flat compound, what is the no load voltage first? Same or not? Yes, for every compound, no load or full load or that is over compound or flat compound or under compound, no load voltage same for all. What is that? 200 volts. That is E. Okay. Now full load. Directly we are taking full load condition. In order to get flat compound generator, previously we applied high value of RD, very high RD. That's why ISC also very high. Now what we do is, let us reduce the RD value, little reduce. If RD reduce, what is ID? Observe the figure. If you reduce the RD value, ID will increase or not? Yes. If resistance decrease, current through the path increase. Whenever ID increase, what is ISC? Decrease, because same current we are assuming full load current. That's why whenever ID increases, your ISC will decreases. Okay. If RD decrease, ID increase, ISC decrease. Previous ISC how much? Very high. That's why series flux is very high. That's why overall flux is more EMF induced. This much is the full load voltage. But now as ISC decrease, what is the series flux? Little decrease. Therefore, total flux is same 5SH plus 5SA. Same, sum of these two only, but overall flux decreases. As flux decrease, what is EMF induced? Tell me, what is EMF induced in generator now? Let this EMF is 210 volts. Previously, how much EMF we taken? 240 we taken. In that, some voltage drop, 10 volts drop, 230, full load voltage, terminal voltage. And now, as total flux decrease, EMF decrease to 210, for example. Now, if it is EMF, what is the full load terminal voltage? Less than that. So, same 10 volts drop, I am considering 200 volts. So, now, no load voltage is 200, full load voltage also 200. No load is 200, full load also 200. Then what is the characteristics, how we draw? See here. For flat compound, no load is 200, full load is 200. This is full load voltage. This is for flat compound generator. Clear? How we are achieving flat compound? By adjusting the RD value here. By adjusting RD, your series flux will change. Series flux we are adjusting. Like that we get the voltage, flat compound. Okay. Now similarly, try to observe. Similarly, try to observe under compound generator. Under compound. Now you can understand what we have to do for under compound. What we have to do for under compound. Previously, what we did here, reducing diverting ratios. For under compound, still reduce the RD value. No load voltage is same. No load voltage is E equals to 200 volts. Now full load. Full load. If full load is applied, let us adjust the RD value, still decreases. Then what is field current ISC? Still decreases. Why decreases? If RD decrease, current ID increase, but ISC decreases. Whenever ISC decrease, what is the overall series flux in generator? Decrease. Then total flux in series generator, total flux in compound generator 5SH plus 5SC. The overall flux little decrease compared to previous. Total flux now still less, still reduces. Then what is EMF induced? What is EMF induced? Previously we taken 210. Now the EMF induced is less than that. So I'm assuming some 205 volts. 205 volts. Still voltage reduced. Then what is the full load voltage? Some voltage will drop. So same 10 volts drop I am considering. That's why 195 volts. This is the full load voltage. This is the no load voltage. Now no load voltage, full load voltage, you try to draw in the graph. Now in the graph, this is no load voltage 200, full load voltage 195, means less than that. This is 195. This is for under compound generator. So over compound characteristics, flat compound, under compound characteristics. So clear how we are getting this? All of you. So by adjusting the RD value, your series flux changing. Whenever series flux changing, your EMF in generator change, and output or voltage across the loads also will change. That is, we are drawing in every case here. These three are in cumulative case. Flux is additive here, additive. Now we will go to differential compound generator. So directly what happens differential compound, tell me. If it is differential compound, for differential compound generator, if it is differential, no load voltage how much? Same. No load voltage is same, 200 only. Now full load case. Full load case. Under full load, load connected. Now shunt field is there, series field also there. What is the total flux in differential? 5SH minus 5SH. So for differential compound, no need of RD, only one. Directly whatever is there, fixed it is 5SH minus 5SH. So whenever load increases, generally no load to full load, when load increase, what is the load current increases? If load current increase, what is the series flux? Observe the figure. If load current increase, directly no RD for this. Remove RD here for series generator. Then if load current increase, directly series flux increase. Series flux increase. Then if flux increases, what is the total flux? Decreases. 5SH almost same, it won't change. But series flux only variable because load is variable there. That's why 5SC increases. Overall flux in generator decrease. Then what is EMF in generator? Also decrease. If EMF decrease, what is the terminal full load voltage? Also decrease. So among all DC generators, the least full load voltage in differential compound. Very small voltage under full load because the total flux is difference. Very low voltage you will get at the full load condition. Very low voltage. So if you draw in graph for differential compound, no load voltage is same, but this is the full load voltage. This is for differential compound generator. Okay, very low voltage under full load condition. Why very low voltage? Flux is difference. If load increase, series flux increase, the difference of the total flux decreases. Whenever flux decrease, EMF decrease, your terminal voltages also decreases. This is the lowest full load voltage. Okay, clear all of you now? Yes, differential compound, no RD, because differential compound only one type. Cumulative three types. In order to get the three types, we need RD there. But for differential, only one fixed. That's why we no need to place RD there. For differential compound, remove RD, not required. Now, what is the application of over compound generator? Application of over compound generator. See, if you observe over compound characteristics, what is the nature of the over compound characteristics? Rising or not? Rising, 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 rising. Slightly rises. Wherever there is rising characteristics, that generator suitable as booster. That is suitable as booster, like series generator. Okay, series generator rising characteristics. So we use for booster, that is same as it is this. And flat compound means no load voltage, full load voltage, almost constant. Same means it is a perfectly constant voltage. Shunt generator almost constant, little drop in voltage. But flat compound generator is the perfectly constant voltage from no load to full load. But we don't use this. We use shunt generator only. Why? Because in flat compound, no load voltage, full load voltage may be same, but in between its voltage increase. At half load, assume that it is half load, current is half. At this condition, the voltage of flat compound little increases. Voltage increases little. Suppose if it is a high voltage, the load may damage. That's why we don't use flat compound generator. Only no load condition, full load condition only, it is having constant voltage. But in between little rises. Next, under compound generator. Under compound generator voltage is almost like shunt generator, but better than shunt generator. This generator will give almost constant voltage. Suppose shunt generator no load voltage is 200 volts. Full load voltage of shunt generator is 190 volts. Let. But in under compound generator, no load voltage is 200, full load voltage is 195. How much voltage drops in this? 5 volts only drop. But shunt generator, how much voltage drop? 10 volts drop is there. More voltage drop in shunt compared to under compound. So under compound is the perfect one if you want almost constant voltages. So wherever constant voltage, that is like shunt generator applications, same applications like lighting applications or auxiliary power supply or battery charging or exciter for field windings, under compound also suitable. Now differential compound generator, where it is suitable. This is the only generator suitable for welding application, DC welding. Differential compound generator is the only one generator suitable for welding. No other generator suitable for welding. Suppose by mistake you are using separately excited generator for welding, immediately your generator will burn. Or you are using series generator for welding, immediately it will burn. If you are using shunt generator for welding, what happens? If we use shunt generator for welding, what happens? It will damage or it is suitable for welding? Tell me. It will damage or is it suitable for welding? Yes, it is a self-protected. It is a self-protected. It won't damage, but it is not suitable for welding. So why it is not suitable? I will show you the reason. It is self-protected, no damage to shunt generator. It won't damage also. If you use by mistake for welding, it won't damage. It is a safe, but welding not possible with that. So how it is, I will show you here. Observe. So after this, we take break. See, let us consider a differential compound generator. First, I will take shunt generator so that you will understand clearly. So taking a shunt generator. Now welding, it is using for welding purpose. Shunt generator, for example, we are using for welding. Welding means what we weld? Metals, plates or rods, anything. Suppose I need to join these two plates. For example, I need to join these two plates using welding process. So how we do welding? There are two terminals, plus minus. In that one of the terminal we connect with one plate directly, and to the other side we do we connect a welding material or welding electrode, and here we do welding process. See, IA, ISH, IL, load current. This is EMF induced in generator. And what is the terminal voltage during welding process? Once you touch for welding, voltage 0. Why voltage 0? Once you touch the two plates, that is with welding process, welding material, voltage is 0, means it is a short circuit condition. Short circuit only because metals almost 0 resistance, very low resistance. Then it is plus minus acting as short circuit. Voltage is 0. If voltage 0, what is the armature current? Eg minus 0 by Ra. Now actually current should be very high, but it won't be very high. Why? Because when voltage 0, ISH 0. When ISH 0, what happened? If ISH 0, flux is 0, EMF is almost very small residual voltage, whatever we have seen now. So armature current is very low value. This much current is not suitable or not sufficient for welding. For welding, we need some high current for weld, but this much current is not at all sufficient. So no damage to generator. At the same time, it is not suitable for welding. Now let us take a differential compound generator. For example, same. So I'm taking a short shunt differential compound generator it is. Now we need to do welding same as it is. These two plates we need to join. These two plates we need to join with welding process. Same procedure. Connect minus terminal to one plate, and this is connected to a welding material here. Now once you touch for welding, see EG, EMF induced in generator, IA, ISH, this is IL. Now in this case, once you touch, what is the voltage here? Also 0. During welding process, always terminal voltage is always almost 0. If voltage 0, what is the current IA? EG minus 0 divided by RA here plus RSC also there approximately. Okay, IA, what is KVL equation? EG equals to V plus IARA plus ILRSC plus brush drop. Then if you find IA, EG minus 0 by RA plus this is also there, small resistance drop. So I'm neglecting the small resistance drop. Directly I'm taking RA plus RSC. If it is long shunt, you will get RA plus RSC, long shunt case. Approximately I'm taking. And this current is not small current, this is little high current. So first of all, in differential compound, EG proportional to what? Phi SH minus phi SC, difference. Whenever you touch it is here, what is the load current? This current is trying to reach very high current because voltage 0, short circuit. Now whenever current is increasing, what is the suddenly series flux also? This flux proportional to current here. Series flux also increase. Whenever series flux increases, what is the overall flux? Decrease. Then what is EMF? Decrease. Then is it very low EMF or there is some proper voltage? It is not like shunt generator. When voltage 0 in shunt, flux 0, EMF almost residual voltage, very less. But in differential compound, as series flux is trying to increase, because of the difference of the flux, EMF decreases. But this EMF is not nearly 0 or residual. This is little high voltage because phi SH will not become 0 completely. It is there. So phi SH minus phi SC. Overall flux is there some value. EMF little decrease. EG little decrease. Current little limited. But this current is not very low value. Okay. Automatically current is limited in differential compound. It is not very high current and it is not very low current like shunt generator. Actually short circuit means high current, but it won't go high value because the series flux increase, overall flux little decrease, EMF also decrease. So current is limited, and this current is not very small value like shunt because there is some proper voltage in this. This current is sufficient for welding purpose. That's why differential compound generator only suitable for welding application. Shunt generator are separately excited also not suitable. If you short separately excited, high current will flow. It will damage. But in differential compound, if you short also, current is limited because of difference of the flux. And this current is sufficient for welding process. Okay. Differential compound is suitable for welding applications. Okay. So don't saturate. We take break here. So take a break. After break, we see voltage regulation. Then we go to characteristics of motor. Before going to characteristics of motor, we see some questions related to motor, which are interested things. Okay. Some interest we have to bring again. So we'll see with questions only interest. Take a break now. Take 20 to 25 minutes break. See the question. The external load characteristics of a DC generator at rated speed is assumed to be linear. The load circuit having only resistance when the load current is 50 amperes, means this is the load current, this is the external voltage, terminal voltage. Okay, the value of load resistance will be dash. The value of load resistance will be dash. How much? Simple one. Easy question. We need to find the value of load resistance. Load resistance is nothing but voltage across the resistance by current through the resistance, that is IL. At what current? 50 ampere. So load current 50. Whenever load current is 50, what is the corresponding voltage? It is linear. At no load, 100 volts. At full load, let 100 ampere, 90 volts. At half full load, what will be the voltage? It is exactly 95, because linearly changing, no? That's why whenever the load current is 50 ampere, then the voltage across the load is 95 volts. From the characteristics, it is. From characteristics. Now substitute here 95 by 50. Nothing but nearly 2 amperes, that is 1.9 ohms. 2 ohms, nearly, approximately it is 1.9 ohms. Okay, 1.9 ohms is the load resistance. Voltage how 95? That's why, see, observe the characteristics here. At 0 ampere, voltage is 100. At 100 amperes, voltage is 90. That is given in characteristics. Now 50 amps means it is exactly at center of this characteristics. Linear, no, it is. Then approximately how much it is? 95 only. 95. That is voltage across load 95 divided by current, load current is 50. Okay. 1.9 ohms is the answer. Yes. Right. Next, voltage regulation. Voltage regulation. What is voltage regulation? So this is we have in transformers and also generators, synchronous generator and also DC generator. In all, we have this voltage regulation topic. What is voltage regulation? Simply, it is the change in voltage across the load. Same definition, everything same in transformer generators everywhere, but only difference here is in DC generators, the voltage regulation does not depends on the load power factor. So if you remember in transformers, voltage regulation changes based on the load power factor. We have seen three cases: lagging power factor, leading power factor, and UPF case. There is positive regulation, zero regulation, negative regulation, like that. Okay. But in case of DC generator, it doesn't depends on load power factor because there is no load power factors here. Only one load UPF. But where it depends now? It depends on type of generator here because in DC we have different types again: shunt, series, compound, again in compound, over compound, flat compound, like that. That's why it depends on the type of generator. Okay. First, let us consider a shunt generator to define this. Taking a shunt generator. A shunt generator. Let it is load. First, switch is initially under open condition. Let us place one voltmeter here to measure how much voltage is there across the load. Initially switch open condition. Then how much EMF will, what is the voltage across this load? Voltmeter will read how much voltage. Suppose EG is 200 volts. EMF induced in generator is 200. Under open condition, switch is open condition or no load condition, how much this voltmeter will read? Same 200. That is called no load voltage. Voltage across the load under switch open condition, that is no load condition, the voltmeter reading 200. That is called no load voltage. What is the no load voltage? No load voltage equals to 200. That is nothing but EMF induced in generator only. Now apply or close the switch here. Switch is closed. Once switch is closed, load is connected. Assume that full load is connected. Now under the full load condition, what is the voltage across this load? The voltmeter will read a voltage of V equals to full load voltage. That is, if 200 volts is the no load voltage, whenever there is a load, current is flowing. Due to that current, some drops will take place in armature, voltage drops. So remaining, you will get some less than 200. For example, let 190 volts. The full load voltage is 190 volts. Now, what is the change observed across the load from no load condition to full load condition? Under no load, it is 200. Under full load, it is 190. What is the change observed? 10 volts is changed. That is nothing but the voltage regulation of this generator. That is voltage regulation. Write the definition. The change in voltage, it is the ratio of, write like this. It is the ratio of change in voltage across the load from no load to full load. No load to full load to the full load voltage. Okay. So draw this. Now we have to see the regulation for different types of generators. So for that, we need to draw the characteristics only, because all characteristics, no, characteristics of all generators in one graph we take. Okay, from there we will see what is the regulation for each generator right here. Starting external characteristics of all generators. External characteristics of all generators. External characteristics is drawn between V versus IF. Okay. Now considering, so already we know this. Under no load condition, what is the voltage of shunt generator, separately excited, and compound generators? Rated voltage. But what is the voltage for series generator under no load? A small voltage. Only series generator voltage is small under no load condition. No load means current zero. But remaining all generators will have some voltage. This is the no load voltage for. So taking same voltage for all generators. Considering same voltage for all generators. Okay, and this is the no load voltage of series generator. Only for series voltage is less. Remaining all will give some rated voltages. Now, first over compound generator. This is over compound. This is flat compound. This is under compound. Okay, voltage for over compound generator, flat compound generator, under compound generator. After that, which generator will come? After this, separately excited generator will come. Separately. So why it is, I will tell. This is separately excited generator. After that, shunt generator. Slight difference, but we are drawing like this. This is for shunt generator. Okay. After that, differential compound generator. Very low voltage under full load for differential compound. Whatever we have seen already, same I am drawing again. Differential compound. But what is the old characteristics of series? Rising. No load to full load. This is the full load point. Consider this is full load. Full load it is. Full load current. Only for series generator, characteristics rises. Let this is the voltage for series generator. Okay, same characteristics I drawn in one graph for all generators. That's it. Now from this we need to define. This is no load voltage. These are the full load voltages. These are the full load voltages. If you observe here, full load voltage of separately excited generator is greater. This is separately excited. Concentrate here. This is the full load voltage of separately excited generator, which is greater than shunt generator. Why this is? Because observe here itself, I will show. Take a shunt generator, for example. Shunt generator. Now, in case of this is terminal voltage. Whenever load increases, IL increase, then what is the terminal voltage? As load increases, voltage decrease. Okay, load generally terminal voltages will decrease. Generally, voltage will decrease at load if load is increasing. At the same time, as terminal voltage decrease, what is the field current? Decrease. Field current will decrease. Now, what is the flux in generator due to this? Decrease. Due to that little EMF drop, so overall voltage little drops. But in case of separately excited generator, it won't happen. In case of separately excited generator, the drop in voltage is not that much, because separately excited means what is the flux? 100% constant, no change in the flux. Even load increases. Even if you increase load, IL increase, EMF no change. Same EMF will be there. Only terminal voltage little decrease. but the drop in voltage is more in shunt generator because of drop due to field current, which causes drop in flux. That's why EMF still little reduced. If you take no load voltage of shunt generator is 200, full load voltage of shunt generator is let 190 volts, and no load voltage of separately excited generator 200. Full load voltage of separately excited will be 195. This is more understanding now. There is a drop in field current here, but there is no drop in field current in separately excited. That's why the separately excited voltage little higher than shunt. Clear now? Why we have taken? Because this order important. The voltage regulation order. So we will see now. The voltage regulation order is important here. If you don't know which is first, which is next, you cannot find what is the order of regulation. That's why this characteristics order important first. Okay. Now we will write one by one here. First, voltage regulation of series generator. Is it positive or zero or negative? How to find voltage regulation? E minus V. So you write here the percentage regulation formula is no load to full load ratio. No, it is E minus V divided by V into 100. No load to full load to the full load voltage. Now substitute. Regulation is E minus V by V. Simply it is proportional to difference. No load voltage, full load voltage difference, whether it is positive or zero or negative. Now observe from the graph for series generator. What is the no load voltage of series generator? Very, very small. Let 10 volts it is. No load voltage is 10 volts. What is the full load voltage of series generator? This much. Let 220 it is. Now no load is 10 volts. Full load is 220 volts. Now 10 minus 220 means almost 100% negative. 10 minus 220 by 220. 10 minus 220 by 220. How much it is approximately? Nearly minus 100% or not. Yes. So regulation is negative, highest in the sense in terms of magnitude 100% it is. Negative regulation it is. Okay. Now in the same way, next, voltage regulation of next over compound generator. Over compound generator. Tell. You just check no load voltage, full load voltage, these 2 points. You will get the answer. No load voltage 200. Full load voltage more than that. No load is let 200. Full load is 210 it is. Means more than 200. Then what is the regulation? Negative. But not highest. Negative, low value. Understanding? Next. Voltage regulation of flat compound generator. What is the regulation now? No load voltage 200, full load voltage also same 200. 200 minus 200, 0. So regulation is 0. Next, similarly, voltage regulation of under compound generator. What is that under compound? This is under compound, this one. For under compound, no load is 200, full load is less than that, let 195. Then what is the regulation? Positive. 200 minus 195 means positive voltage. That is positive regulation, low value it is. Low regulation, positive, low. Just like in transformer voltage regulation curve. Same curve you will get in alternator also. Same regulation curve. Okay. However, there is changing value, positive regulation, low value, high value, maximum value, zero regulation, negative small regulation, negative highest regulation. So same as it is you will get here. Okay. Next, voltage regulation of separately excited generator. Separately excited generator. Positive or not? Yes, positive only. This is also low value. Next, voltage regulation of next one is shunt generator. What is this value? Positive regulation only because no load is 200, full load is less than that. Okay, low value it is. It is also low, 5 volts, 10 volts, these are all low regulation. But observe voltage regulation of differential compound generator. What is this? Tell me. Voltage regulation of differential compound. No load is 200. Full load voltage of differential is let some 50 volts. Now, what is the difference? 200 minus 50 means 150 volts difference. So this is positive highest regulation. Positive highest value it is. These three almost near with little small variation is there. Now, out of these three, what is the order of voltage regulation? Voltage regulation. Which is highest voltage regulation out of these three? Out of these three, this one, this one, this one. Which is the highest regulation? Shunt generator is the highest regulation. Okay. If you write the order in these three generators, we get the order of voltage regulation. Order of voltage regulation. Only for the three generators I'm writing because they are almost near. That's why voltage regulation of under compound generator. Voltage regulation of under compound generator is less than separately excited generator is less than shunt generator. For example, if under compound regulation is 4%, it will be 5%, it will be 6%. Like that, little small variation, not big variation it is. 1 volts, 2 volts drop variation will be there. Okay, this is order of voltage regulation. Just example I given, not always 4, 5, 6 like this. Okay. See, what is the need to find regulation? So already you should know from transformer or alternator point of view. Why we are finding regulation? Tell me. The reason to find voltage regulation is, suppose you know for this much load power factor, the regulation of generator is 4%. Means 4% voltage drop. If regulation value you know 4%, that means 4% voltage drop will be there in generator. Now, based on that voltage drop, we will increase excitation of the generator. We will increase excitation of generator. When excitation increase, flux increase, little EMF increase. How much to be increased? Whatever drop is taking place, that much EMF we have to increase. For that reason, we should know how much regulation is there first. That is the reason we are calculating to maintain the proper voltages at loads. To maintain proper voltages at loads. Yes, very good. So all of you remember this graph, these external characteristics of all generators and this regulation, because particularly in objective type like in prelims and also competitive examinations only, mostly we are getting questions on this. But for GATE, it is not that much important. Okay, for GATE, there are some topics important. But for engineering services and competitive examinations of your state boards and all, everything is important because they will fetch where to give. But GATE is not like that. GATE people will think where we have to concentrate. But engineering services and any other examinations, you have to be covered each and every topic. Okay. So this is important. So here, this voltage regulation, you no need to remember if you remember this graph. That characteristics, if you remember enough, at any time you can write what is the regulation of the generators. Completed. Yes, you can write. That depends on the government provided non-local category. If they provide, we can write, otherwise we cannot. Right now, DC motors. From now, DC motors. Motors only we discuss from now. That is characteristics of motor, and after that, speed control of motors. Okay, right. DC motors. So before going to characteristics, first you should know what are the important terms in motors. Two important terms are there in motors. One is back EMF of motor, and second one is torque of the motor. So first, the back EMF of motors, EB equals to, what is the equation? Z phi n into P by 60A. This is back EMF, EB, Z phi n into P by 60A. Now in this equation, I will convert this equation in one standard form, that is, observe, EB equals to ZP by A. So I taken outside ZP by A because they are constant. 60 also constant. Now I will divide with 2 pi here, and I will multiply with 2 pi here into n by 60, and into remaining is 5. Observe the equation once. Same equation or not? Just 2 pi multiplied and divided. 2 pi is multiplied and divided. No change in the value. Now this EB is nothing but this ZP by 2 pi A, whatever is there here. This is called motor constant, Km, into this 2 pi n by 60 we can write as omega in terms of radians per second. Omega, this is flux of the motor. Therefore, this is one standard form of equation where Km is called motor constant or armature constant. This is called motor constant or armature constant. See, sometimes in particularly AP, there is in one of the examination transpo, they asked directly based on this Km only. If you know about this motor constant or armature constant, then only you can solve that question. Otherwise, we cannot. Remember, motor constant or armature constant. Its equation is Zp by 2 pi. So this term we call motor constant. Now, this is one equation, and from this equation, EB proportional to Km constant. In omega, 2 pi by 60 also constant. Only variable is n into 5. So this is one most important relation. This is one equation. And the second equation is torque. That is the torque developed in motors. The torque developed in motors equals to mechanical power divided by omega. What is the mechanical power equation? EB into IA by, mechanical power is this, EB IA by omega. EB means this one, substitute here, Z phi n into P by 60A into IA divided by omega means 2 pi n by 60. 2 pi n by 60. Now in that n by 60 cancel, n by 60 cancel, and remaining are, right up to this next page we go. EB I substituted just EB equation. Omega means 2 pi n by 60 in terms of RPM. Therefore, the torque equals to Zp by 2 pi A into 5 I. So it will be left in this. And here also we can write Zp by 2 pi M is motor constant or armature constant into 5 I. This is one important relation. And in this, Km is the constant, torque is proportional to product of flux and current. So this is one of the important equation, second. So these two equations will play the major role in total DC motors. Speed control methods completely depends on these two equations, equation 1 and equation 2. Very, very important. Now we will see some questions. So that questions completely depends on these two equations only. Okay, first right up to this. Take the equations. Omega means radians per second. N, capital N is the RPM, rotations per minute. Yes, this is valid for generator also. These expressions in generator, EG, EB, in place of EB, EG will come proportional to N phi. In case of generator, same equation, torque proportional to phi Ia. It is valid for generator also. Same equation valid for generator also. Okay. So write one question. Right question. A DC shunt generator. A DC shunt generator supplying power to bus bar. Supplying power to bus bar. If suddenly the prime mover of generator fails, the prime mover fails, then it behaves as dash. Then it behaves as dash. Answer this. So only two options. Motor in same direction. Second, motor in opposite direction. Motor in same direction, motor in opposite direction. How it behaves? Tell me. Generator previously supplying power to bus bar. Bus bar means grid connected it is. Now, due to some problem, the prime mover of generator failed. Then how it behaves? As a motor, definitely in same direction it rotates or it rotates in opposite direction. What is the answer? Okay. So most of you giving opposite direction. Some of you also given same direction. Yes, answer is same direction it is. It works as motor and rotates in same direction. Okay, see how it is. See how it is. First, let us consider there is a DC shunt generator. A DC shunt generator supplying power to bus bar. Let this is the bus bar. This is bus bar. Grid connected, constant voltage it is always. Supplying power to this. Now, as a generator, I am rotating clockwise direction with a prime mover at some speed n. So generator means what is the torque developed in generator always? Same direction or opposite direction? In a generator, if it is rotating clockwise, internal torque will be opposite direction. Now what is the torque relation? Proportional to product of flux and armature current, phi Ia. Okay, this is generator. So all of you take this figure first. All of you take this. Then we change this one. Now it is a generator supplying power to bus bar. Take the figure. In the same diagram, I am changing now. Completed. See now mechanical input or prime mover input fails. Means there is no input now. Mechanical input is totally zero. If there is no mechanical input, definitely it will not work as a generator. Now, as it is connected to bus bar, it will take power from bus bar or not? Yes. Now, same generator will consume power from bus bar. Current IL reverse. IA also reverse. But what about ISH? Remains same it is. Whenever ISH is same, flux is remains same. So the new torque generated is product of flux. And what is the current now? IA reverse. Previously IA supplying, now IA taking minus IA. Then what is the torque? Positive negative become negative. Means there is a change of torque. What is the torque previously? Anti-clockwise. Now what is the new torque? Clockwise direction. Now in which direction motor rotates? Motor always rotates in the direction of torque. If torque is clockwise, it rotates in clockwise only. So the torque we got in clockwise direction, it rotates in same clockwise direction. Generator also rotating clockwise. Now motor also rotating in same direction. Okay. Answer is it works as motor in same direction. Next question. Next question. Same model, one more question. Try to answer this. A series generator supplying power to bus bar. Supplying power to bus bar. If prime mover fails, then it behaves as dash. It behaves as dash. Tell answer. Same, two options. Motor in same direction, motor in opposite direction. How it rotates? Series generator it is. Supplying power to bus bar. Supplying power initially. Current direction is this. First generator, I am rotating clockwise. Torque in generator anti-clockwise, opposite to rotation. Current direction is this. Okay. Torque is proportional to product of flux and IA. It is a anti-clockwise now. Positive means current is supplied. Generator case it is. This is generator diagram. Now, prime mover input fail or mechanical input fail. Remove this. So I'm removing. If mechanical input is 0, now the same machine will take the current or not? Yes. Now current direction IA reverse. Whenever IA reverse, what happens to torque? Flux also proportional to IA in series machine. As flux proportional to IA, flux also reverse, current also reverse. Overall, it is IA square. IA is negative. Minus IA whole square means torque is same, no change. That is previously positive, now also positive. Torque remains same. Whatever is there in generator anti-clockwise, same torque will be there now also. Now in which direction motor rotates? In the direction of torque. Torque is in anti-clockwise direction. That's why motor rotates now anti-clockwise. But before that, there is a braking operation. Why braking? Previously generator rotating clockwise. Whenever mechanical input fail, during that instant, motor speed first reduces to 0. Motor speed reduces to 0, then it starts rotating in reverse direction. But finally under steady state, it will rotate in opposite direction. So it behaves as motor, rotates in opposite direction. Rotates in opposite direction. Okay. Opposite direction of generator, that is. Opposite direction of generator. Next question. Why IA square? Because flux proportional to IA. Flux proportional to IA square. Okay. Next question. Try to answer this. A cumulative compound generator. A cumulative compound generator supplying power to busbar. Supplying power to busbar. Supplying power to busbar. Okay. If suddenly prime mover fails, then it behaves as dash. Then it behaves as dash. Options are cumulative compound motor in same direction. Second, cumulative compound motor in opposite direction. Next, differential compound motor in same direction. Next, differential compound motor in opposite direction. In opposite direction. What is the answer? What is answer? See, in shunt generator, no, flux is not proportional to IA, no, flux proportional to ISH. That's why we don't take in here. ISH is not reverse, that's why flux also same only. But series only flux proportional to IA. Okay. Cumulative compound motor in same direction. On differential compound, same direction. See, the answer for this question is differential compound motor in same direction. Option C is correct. Okay, so let us consider a cumulative compound generator first. Cumulative. See, you can answer these questions easily if you remember the 2 points. What are the 2 points? Generator torque opposite direction, motor torque same direction. These 2 points enough. And that relation, torque proportional to product of flux and current. You know these points enough. Now I'm taking a cumulative compound generator. This is a cumulative compound generator supplying power to busbar. Okay, like this. Cumulative compound generator means what is the total flux in this additive? This is IA, IL, ISH. So torque in cumulative compound generator proportional to product of sum of shunt and series into IA. This is for compound cumulative compound generator. Torque is anti-clockwise direction because we are rotating clockwise. If generator rotating in clockwise, internal torque will be opposite direction. That is cumulative compound generator. Okay, generator it is. See, generator series flux proportional to IA here. Now let us remove the mechanical input or prime mover. Remove this. Prime mover failed. Now it can draw power from busbar or not? Yes. Now it will take the current from busbar. IL reverse. IA also reverse. ISH same. That's why phi SH remains same, but IA reverse series flux only reverse. Torque proportional to phi SH remains same, but phi SC become minus phi SC. IA also reverse, so minus IA. Now what is the overall torque here? Positive or negative? Phi SH minus phi SC means differential it is. Now it is acting as differential. This is differential and minus IA. This is positive, this is negative. Overall, positive, negative means negative. Torque will reverse. Generator torque anti-clockwise. Now motor torque will be clockwise direction. This is the torque produced. T. Okay. This is the torque produced. T. Therefore, it is running in same direction as generator, clockwise only. But which motor it is? Differential, no? Because 5SH minus 5SC. That's why it is a differential compound motor and rotates in same direction of generator. Answer is DCM, same direction. Clear now, all of you? See, whatever the equation we have written, that is internal torque, not prime mover torque. Okay, that's why we are considering internal torques only. You consider short shunt or long shunt, any shunt, answer is same. We will get differential compound only. Will get. You check one if you want. You check by taking short shunt. Okay. Now another question. Last question in this. One more question. Read the question. A differential compound generator. A differential compound generator supplying power to a load. If prime mover fails, it behaves as dash. It behaves as dash. What is the answer? If prime mover fails, it behaves as dash. No, series flux generally less only, because we will design like that. Series MMF or flux is generally less practically compared to shunt always. That's why we take always shunt is more. What is answer for this? Answer for this. Okay, so most of you giving cumulative compound same direction, differential compound. Okay, but very few given. Yes, very good. Very few given the right answer. So those who are giving cumulative compound or differential compound, read the question one more time. Read the question one more time and then answer again. Concentrate in the question only. Yes, very good. Yes, the answer is motor comes to stop. Not motor, machine comes to stop, because generator, it is supplying generator. Okay, generator supplying power to bus bar. If prime mover fail, it stops. Why? It is supplying to a load, not bus bar. I did not given bus bar right now, but you are thinking same sequence like previous questions. Okay, it is a load. Load cannot supply back. Whenever prime mover fail, load cannot supply. Bus bar can supply, but not load. Resistive load will supply to work as a motor? No. So it comes to stop. If it is supplying power to bus bar, then what is answer? Cumulative compound motor in same direction. That is correct. Okay. If it is bus bar, answer is CCM in same direction. Okay. Clear all of you know? Next question. What is answer for this? What is answer for this question? See, a cumulative compound DC motor runs at 1500 RPM on full load. If its series field is short circuited, its speed is dash. Cumulative compound motor. So let us take the figure. This is, assume that this is a cumulative compound motor. It is a cumulative compound motor. Motor means we give supply to this and it is drawing a current. This is armature current, field current, load current. Now this motor is running at a speed of 1500 RPM. From the previous equations in the starting of motor I given EB proportional to N5. From this equation, N proportional to EB by 5 or N is inversely proportional to flux mainly. In cumulative, what is the total flux? Sum of the two, phi SH plus phi SA. So when both are there, see series flux, this is shunt. When both are there, the speed is 1500. Now what is given in the question? Series field is short circuited. So you short this. Whenever series field shorted, then is any current will go in the field winding here? No current. Then what is the series flux? Zero. Series flux is zero. Then what is the net flux of the motor? Only phi SH. Previously both are there, but now only phi SH means total flux decreases. Then what is the speed of motor? Increases. The speed of motor increases. Okay. Clear now, all of you? See, whatever given in the question, you put that is in the diagram, then only you will get idea, but don't solve directly these questions. Put it's in the figure, you will get the correct answers. Torque also changes, but we are considering directly this equation. Torque also will change accordingly. Now don't say that torque is proportional to total flux phi SH plus phi SC into IA. Okay, then whenever series flux is zero, total flux decrease, torque decrease, speed decrease. Don't say directly this, because this is the important relation. Maybe you are considering the torque is decreasing, but torque will not decrease. Torque also increase. How it is in the next coming questions, I will show you. Just meanwhile, just remember this equation enough. Okay, consider mainly speed relation. In order to say the speed answers, consider mainly this relation. Speed relations only you consider, not torque relation directly. So I will show you in the next coming questions how torque will change. Okay. See this question. A 220 volts 10 kilowatt 900 rpm separately excited DC motor has armature resistance of 0.02 ohms. When the motor operates at a speed and with rated terminal voltage, the electromagnetic torque developed by the motor is 70 Newton meters. Neglecting rotational loss, the current drawn by motor from supply. Current drawn means armature current only, separately excited motor, no? 220. Current drawn by motor we need to calculate. For the supply voltage, 220 volts. Try this question. See, whatever the power rating is there in the question, that is the output power. That is the output power, not input. Always that is output power. And the voltage rating is supply voltage. 900 rpm is the rated speed of the motor. Try this. Simple question. Based on torque equation, completely it is. We need to find armature current. Given the torque is there. What is the torque equation? Mechanical power developed divided by omega. Torque equal to power by omega. What is the mechanical power equation? EB into IA divided by omega. Okay. Now from this equation, we can write EB into IA equals to cross multiply torque into omega. And what is EB? Back EMF in terms of KVL equation, V minus IARA into IA equals to torque into omega. Torque is how much? 70 Newton meters. Omega 2 pi n by 60. What is speed of the motor here? Rated 900 rpm. 900 divided by 60. 2 pi n by 60 it is. Omega means. Now in this equation, supply voltage is there 220 minus IA is we need to calculate. Armature resistance also given 0.02 into IA equals to 70 into 2 pi n by 60. Okay. Only unknown in this equation is IA. So you'll get one equation. Solve that quadratic equation, roots of the IA. Calculate IA from this. Tell me. Find out roots of this. Ax square plus bx plus c formula you get. Find the roots of this IA. Two values you will get. Tell me the two values. Tell the roots of this. What are the roots of this equation? Solve this first. Simplify little and tell what are the roots. What are the roots? IA values. Yes, 30 and 10969. Very good. 10969. Two values you will get 30 amps and 10969. So definitely current is not this much. Thousands of ampere will never design. Okay, this is wrong. So only valid one is in this 30. So the answer is 30 amperes. Option B is correct. The current is not so much high. 30 amps is the answer. Yes, you can substitute options, but that will take, if it is in option D 30 ampere, then it will take so much time. No? If you go like A, B, C, D. Anyway, you can do this. Right. Next question. Write this question. Write the question. A DC shunt motor running at rated speed. Running at rated speed. Okay. If the shunt field gets open circuit. If the shunt field gets open circuit, due to some problem, it is open. So don't ask how it is open, why it is open, who is open that. So just, it is open. So you follow the question and answer. Then only your concept will build and you will get a good rank. Otherwise, if you keep on thinking here, why it is open, how it is open. So this type of doubts you should not come. Okay. Follow the question, give the answer to that. Then only we get good ranks. Otherwise, if we keep on thinking, no, we cannot get any rank. If the shunt field gets open, then the speed of motor is dash. So I will tell you here both theoretical answer, practical answer, both I will give you. So first answer theoretically. If the shunt field gets open, then the speed of motor is dash. Speed of motor. Options. Increased speed. Increased speed. Second, decreased speed. Decreased speed. Third, dangerous high speed. Dangerous high speed. Fourth, comes to stop. Comes to stop. Okay, try to answer this. Okay. Okay. So mixed answers. Most of you given dangerous, most of you given comes to stop. Okay. So anyhow, the theoretical answer for this question is dangerous high speed. The theoretical answer is dangerous high speed. If it is a practical question, answer is comes to stop. So both I will give the reasons how it is. Practical. Suppose you face this question in interview, no? Then you ask interviewer back again. You need a theoretical answer or practical answer. Theoretical answer is dangerous high speed. Practical answer is comes to stop. That is also I will tell you how it comes to stop practically. And theoretically means with equations we will consider that dangerous high speed it is. So how it is observe now. There is a DC shunt motor. While learning particularly machines, you should learn practically also. Then only subject will build. But anyhow, those who completed engineering, there is no chance at all to see practically now. Practically, we have to observe this one in the lab. Whenever shunt field open, how open? You can easily open in the lab panel boards. So there you remove that wire in the field winding, open circuit. If field winding is open, what happens to the motor? You can observe practically there. But right now, those who completed, we cannot see. I also cannot show you. But practically, I will give how it will comes to stop. Listen. First, Let us consider a DC shunt motor. Applying some voltage, rated voltage. Now motor is rotating at rated speed initially. IL, IA, ISH. Motor is running at rated speed. N. Now suddenly the shunt field of the motor gets open. Why it is open? Because there are number of turns in this. And in the winding, there is some heat dissipation. Why loss is there? Copper loss. Due to that, some heat dissipation is there. Now let us assume due to that improper heat dissipation in some of the turns, let us suppose at this area, the number of turns whatever is there, they gets melt. The winding gets melt, means open circuited. Melt means what? Open. Copper wire melted. That means open circuit takes place. Then what is the field current? Zero. If it is open, no current will flow here. Open circuit. Field current is zero. When field current zero, what is the flux in motor? Not totally zero. Let us assume a small residual flux is there at that instant. Because of that, now the speed of motor will be dangerous high speed. How it is dangerous high speed? See, whenever there is sudden change, after the sudden change, there is a transient behavior of motor that you need to understand first. Transient behavior. After that, the steady state operation we need to consider. Observe this. Whenever the speed of motor, according to equation, if you see, it is inversely proportional to flux. When there is a flux, rated speed. When flux is almost zero, the speed of motor is dangerous high speed. You can tell directly from this, but you may get doubt how it is, because you will think that torque proportional to flux Ia. Whenever flux reduces to zero, nearly small amount of flux, then you may think torque also reduces. Then how speed increasing? That is a right question only, no doubt. Because torque reducing, then who will drive the rotor? But torque actually it won't reduce. Torque will increases here. How it will increases? Torque increase. Let's see how it torque increases here. Because Ia will increase. How Ia increase? That is also I will show you. Observe. For example, I'm considering one numerical so that you will understand. Let it is 200 volts supply voltage. Let the armature resistance of the motor is some 0.1 ohm and back EMF induced in motor is less than that supply voltage. Let 190 volts. Okay. Just example I given. What is the armature current now with respect to this data? Calculate V minus EB by RA. What is V? 200. What is EB? 190. Divided by armature resistance 0.1 I taken. 0.1. What is that value? Ia equals to 200 minus 190 is 10. 10 by 0.1 is 100 amperes. The armature current is 100 amps. This is under normal rated speed condition it is. This is the current at rated speed condition. Still it is not open. Now let us consider field open. Field open. Then what is the flux? Almost zero, but not totally zero. Small amount of flux is there. Let us consider now the residual flux is, if total flux is 100%, residual flux is 5%, small amount. So now only 5% of flux is there. Only 5% is there. 95% flux is reduced. Now, whenever flux reduces to 5%, what is the back EMF immediately? Because EB proportional to N5. EB proportional to N5. Speed of any motor will not change instantly in the complete universe. Any rotating body, if you take any rotating body, suddenly no body will respond to the changes in speed. So whenever field open, at that instant, speed is rated speed only. So speed suddenly will not change. Now keep that speed is same. But what is the flux now? Electrical quantities will change suddenly, but not mechanical quantities. That's why flux reduces to, how much flux reduces? 95% flux reduces. Only 5% is there. If flux reduced by 95%, how much back EMF reduce? Also 95% reduce. Because EB proportional to 5. Whatever flux is reduced, now what is the flux remaining? 5%. Now, how much back EMF will be there? 5% only will be there. Because flux reduced by 95%. It is also reduced by 95%. Only 5% is remaining. So back EMF reduced. Whenever back EMF reduce, what is the armature current? V minus EB by RA current. Supply voltage remains same, V. But what is the back EMF? Previously back EMF 190. Now what is the 5% of this 5%? Calculate how much? What is 5% of 190? 9.5. Okay, right. Okay. 9.5 or approximately 10 volts it is. For example, 10 volts. EB is only 10 volts. So V is how much V? 200. EB is 10 volts divided by armature resistance 0.1, same. Now 200 minus 10, 190 divided by 0.1. How much it is? 1900 amperes. What is the current previously? 100 amps. Now what is the armature current? 1900 amperes means 19 times the current increase. Or how much percentage it is increased? Nearly 190 percentage. How much flux reduced? 95% flux reduced. But how much current increases? 190 percentage current increases. 190 percentage. Because of that reason, what is the torque now? Increase. Which effect is dominating? Current is dominating here. Flux is reducing, no doubt, but current increases by so much value. Because of the torque is dangerous high torque. Because of this much high torque, now rotor will accelerate like anything. Quickly it accelerates and reaches very dangerous high speed. Okay, it will reach to dangerous high speed. Clear now how torque increasing? Even field is open, flux is almost zero, but the armature current increases to so much high value. Because of the torque increases, speed also increases. Now it is a dangerous high speed. Theoretical answer is dangerous high speed, but practical answer is practical. If you operate this is in your lab, the answer is option D, comes to stop. Can you say why it comes to stop? Can anybody? Why it comes to stop? Can anybody answer this? Okay, very good. At least you are trying to tell something that is required. Yes, very good. So whether it is right or wrong, at least you should you are answering. You people are answering. Very good. Okay. So no problem. You are answering something. Some of you right also, but still that is not completed. That's why you cannot answer. How it is? See here. How we are starting DC motors? Then how we are starting DC motors? By using starter. Okay, starter. DC shunt motor we start generally using 3-point starter. 3-point starter. In this starter, as we are using a starter to start a DC motor, whenever field winding open, the starter will come back to off position automatically. Whenever field winding open circuited, the starter handle, whatever the handle you are moving, suppose we will move the handle from off to on position. If you take the hand outside, it will be in the same position because continuously motor will run now. But whenever field is open, automatically the handle come back to off position. So motor is comes to stop. How it comes to stop? So there, if possible, I will show you in the starters. So at least one starter I will discuss. So there I will show you how the DC shunt motor comes to off position, that is comes to stop. This is by starter operation, because definitely starter required to start DC motors in order to limit the high starting current. Automatically during that it will comes to off position. So how it comes to stop, I will show you in the 3-point starter. Okay. Theoretical answer. So wherever you write examinations, because you should not blame me again whenever you put any wrong option in examination. You said it comes to stop, but dangerous high speed is the answer. That's why I'm saying In all competitive examinations or written examinations, the answer is dangerous high speed only. Theoretically only you should answer. But in the interview stages, if they ask this question, then you have to ask it, whether it is theoretical question or practical question. Practically answer is comes to stop. How it comes to stop, I will show you in 3 point starter. Okay, so clear all of you this point? Yes. With starter, it comes to stop. How it is, I will show you. See, DC shunt motor is not self-protected. Don't confuse. Shunt motor is not self-protected. Shunt generator is self-protected, but not shunt motor. Motor will damage. That point is about only shunt generators. Shunt generator is self-protected, even load increase. But shunt motors are damaged. Shunt motors will damage. Okay, don't confuse. So the characteristics of DC motors are motor characteristics. Next one, characteristics of DC motors. So there are mainly three characteristics in DC motors. They are speed versus IA. Second, torque versus IA. Third, speed versus torque. Speed versus IA, torque versus IA, speed versus torque. See, this is one question in this one. Shunt field gets opened, the speed of motor. What is the speed? Dangerous high speed. Now write one more question in this. One more in the side by, just take here. One more question. In the above question, if shunt field is short circuited, then speed of motor is dash. Speed of motor is dash. Tell me. In the same above question, if the shunt field is short circuited, now you don't get any doubt again how it is shorted. That's why I said whatever is given, you put in the figure. That is given that shunt motor, it is initially rotating at rated speed. Initially rotating at rated speed. IL, IA, ISH. Rotating at rated speed initial. Then speed is proportional to 1/5. Now shunt field shorted. Short this. Across that, put a short circuit. Short circuit. Then what is the armature current? 0. Why it is 0? Voltage source shorted, or current always take the low resistance path, that is this one. So no current will come in armature now. Whenever IA is 0 in the every question, then definitely motor comes to stop. Whenever IA is 0, motor comes to stop. In every question it is sent. You need to check in the question IA is there or not. If there is IA, it will rotate. If IA is 0, motor comes to stop. That's it. Okay. So take care of this type of questions. Just draw the figure and put that is in the diagram and analyze there what is happening. Then you will get the answer. If IA is 0 in the question, motor comes to stop. How IA is 0? How IA is 0 means, see, from whenever supply given here, the complete current will go in the short circuit path only, zero resistance it is. Current always prefers low resistance path, that is zero resistance. So no current will come in armature, 0 it is. That's why motor comes to stop. Okay. Flux also zero. Flux also zero. But previously, even flux zero, it is coming, rotating. But here, torque zero completely because I is zero, na mainly. Torque mainly depends on current. If it is zero, definitely motor comes to stop because torque will become zero. Okay. Now there are three important characteristics: speed versus IA, torque versus IA, speed versus torque. Out of these two we call electrical characteristics. This is called purely mechanical characteristics. Purely mechanical characteristics. And one hint here is you no need to remember three characteristics. Let us remember first and second enough. Third one is same as it is first characteristics. So no need to draw again separately. For every motor it is same. Third characteristics same as it is first characteristics. So why it is I will show you in the characteristics. Okay. So brake required. Okay. So take a break for 20 minutes. Otherwise, you will get saturated, difficult to understand. Take a break and come back. After completion of characteristics, mostly today only we start at least some introduction of speed control of DC motors. Okay. Take a break. Right. First, shunt motor characteristics. Shunt motor characteristics. Separately excited motor we don't see again because shunt motor separately both almost same characteristics. Okay, shunt motor. In case of shunt motor, what is the field current? Constant or not? Yes, ISH. ISH equal to V by RSH. V by RSH. Supply voltage is always constant, DC. Hence, RSH also constant. That's why the field current is constant in this. As field current is constant, what is the flux in motor, shunt motor? Constant. The flux in shunt motor is constant. Now, the first characteristics are speed versus IA. Speed and armature current relation. What is that? Speed proportional to EB by phi. From previous relations, speed proportional to EB by phi. What is the flux in shunt motor? Constant it is. So, N proportional to EB. What is the back EMF? V minus IARA. V minus IARA. Now we need to draw the relation between the speed and armature current. Whenever no load condition of motor means what? What is the no load condition of motor? No load is nothing but, see, in your labs, you do brake test on the motors, brake. Suppose if you don't apply any brake, assume that belt is loose one. That is nothing but no load. So under no load, shunt motor will rotate at some normal speeds only. That is nearly rated speeds. This is the speed of shunt motor under no load. Some 1400 RPM it is rotated. This is the speed of shunt motor under no load condition. Now whenever load on motor increase, load means mechanical loads. If the load increase, the current drawn by motors increase. Current drawn by motors increase. That is IA increases. Supply voltage same. Whenever load increase, IA increase, or whenever IA increases, what is the V minus IARA? Decrease. Because drop increase, that V minus IARA decrease. Means the speed of motor slightly decrease. The speed of motor slightly decreases as IA increase. Let this is full load condition. Full load means rated current. This is no load. From no load to full load, what is the speed of this shunt motor? This is almost constant or not? Yes, approximately the speed of shunt motor is constant. The speed of shunt motor is constant approximately. Negligible drop it is because IARA drop. How much IARA drop? Armature resistance very less than 1 ohm. Current is 10 amps, 20 amps range. So that IARA drop compared to supply voltage is a small voltage drop. That's why speed slightly decrease. Approximately we can treat it is a constant speed motor. Okay, this is the first one. Next, second, torque versus IA. Torque versus armature current. What is the relation between torque and IA? So we know from previous equation, torque is proportional to product of flux and current. Okay. What is the flux in shunt motor? Constant. It won't change. If flux is constant, torque is proportional to IA. Means whenever IA is 0, torque 0. Whenever IA increase, torque increase. That is linear. If IA increases, the torque of motor also increases. So linearly increases. But is it always linear? No. Why? Because whenever IA increase, armature flux increase. Then armature reaction increase. Armature reaction increase. Because of that, reaction increases. Armature reaction is demagnetizing, one of the effect. So due to that, whenever there is demagnetizing effect, then the flux in the motor slightly decreases. Up to that, it is constant. There is no much variation. But whenever current is very, very high, demagnetization is more. Because of that reason, due to armature reaction, from a particular value of current, let from this, the torque slightly increase, but not very high. Linearly, it won't change. After that, saturation, not saturation, this is due to armature reaction. If you consider armature reaction, torque non-linearly increases after some particular current. If it is very high, if current is very high, reaction is very high, more demagnetizing effect. So torque variation is non-linear. Suppose if you don't consider armature reaction, this is the dotted line, continuously linear. This is when saturation is neglected. Whenever saturation is neglected, the torque versus Ia is linear. If saturation, not saturation, armature reaction. If armature reaction is neglected, this is linear. If armature reaction is considered, then the torque versus Ia is non-linear. Okay. Next, speed versus torque. Third one, speed versus torque characteristics. Torque is proportional to Ia or not? Yes. That's why speed Ia characteristics, speed torque characteristics, both are same. However, Ia variation is there, torque also same variation. Okay, that's why when Ia is 0, no load condition, this is the speed of motor. No load condition, the speed of motor is some n. This is the no load speed. Whenever Ia increases, torque also increases, the speed of motor slightly decreases. Okay, same as it is speed versus Ia. These two are same. That's why every time you no need to draw speed torque separately. In the speed versus Ia itself, you can represent torque also here. Both are same almost. Okay. Now, one question. The speed torque characteristics of shunt motor. Shunt motor is similar to which motor? Is similar to which motor? Options: series motor, induction motor, differential compound, none of this. None of this. What is the answer? The speed torque characteristics of a shunt motor is similar to which motor? What is the answer? Tell me. What is the answer? Yes, very good. Answer is option B, induction motor. Maybe you may get doubt how it is, because you have seen torque slip characteristics of induction motor in different way. How it is like this. The torque slip characteristics of induction, torque slip nothing but torque speed, both are same. Torque speed or torque slip, you call torque slip or speed, anything we can consider. How the characteristics we got? So at the time of starting, speed 0 here I'm taking, this is synchronous speed, and slip equal to 1 here, slip equal to 0 here. Now at the time of starting, there is a starting torque for induction motor, this is synchronous speed. The torque slip characteristics will be like this. Okay, this is the torque slip characteristics of induction motor. How it is same is, you should not consider total graph. You have to consider only from this point to this point. That is, this is the no load speed. No load speed is almost synchronous speed. No load speed of induction motor is very near to synchronous speed. Suppose synchronous speed is 1500 rpm. The no load speed of induction motor is nearly that, 1480, 1490. It rotates nearly. Okay, that is the no load speed. And full load speed is somewhere here. This is the full load. Now observe only from here to here. This is the variation of speed torque characteristics of induction motor, only from no load to full load. Now, shunt motor also same or not? Yes. Shunt motor characteristics also same, no change in that. The shunt motor characteristics also same as it is this. That's why both will have same speed torque characteristics from no load to full load operation. Only no load to full load we compare. Now write one question first. One question. Identify speed torque characteristics of shunt motor. Shunt motor. These are the options. What is the answer? Speed torque characteristics of a shunt motor is dash. Which option is right? Yes. So now you are answering because just now I given. Otherwise, most of you may given wrong. Okay, very good. Yes, almost right. Answer is D. Speed torque characteristics of shunt motor is this. So why? Because why I'm giving this one is, don't remember the shape of characteristics. Most of the people will remember this one. Speed torque characteristics of shunt motor is like this shape. Don't remember the shape, because what I given here, I changed the axis here. Torque on y-axis, speed on x-axis. So if you think that this is the shape, this is wrong, because here I given torque and this is the speed. And with respect to torque and speed here, this is correct. What is the meaning of the characteristics first? Observe in this. What is the meaning here? Whenever torque increase from no load to full load, the speed of motor slightly decrease. Whenever torque increase, speed should decrease slightly. Now observe here. Whenever torque increase, the speed slightly decreasing. This is only correct. It is almost same as induction motor or not? See, torque speed of induction motor it is, and torque speed of shunt motor it is. Both are same. Okay. That's why never remember shape of the characteristics for any motor or generator. Remember the equation. At any time you have to draw the characteristics. That's it. Now finally, what is the application of shunt motor where we can use this? As this motor is almost constant speed, wherever we require constant speed, just like induction motor application, you can use shunt motor. Like we can use it is in the lathe machines, but nowadays we are not using it is in lathe machines. Suitable there, but not using. Lathe machines we can use, or we can use at the centrifugal pumps. We can use blowers for constant speed, blowers, etc. So many applications are there like this constant speed. But nowadays we are not using shunt motors. Mostly induction motors only we are using. But at some places we are using universal motor. Like what is that universal motor? Series motor is suitable as universal motor. So I will give the information of universal motor at the last. Okay. So these are the applications of shunt motor. Wherever constant speed is required, there we can use shunt motor. Just like induction motor. Induction motor also almost constant speed it is. Yes. Conveyor belts. These are all applications. Okay. See, what is the motor we are using in the lift? Lifts. Three-phase induction motor we are using. So anyhow, we will see in the later. All of you completed this. See, motor characteristics are not that much important like generator characteristics. So here very less chance to get questions in motor characteristics. Okay, next. Series motor characteristics. In the characteristics, important means series motor only important. Right. Series motor characteristics. Okay. Now speed versus IA of series motor first. Now, first of all, tell me what is the flux in series motor? Constant or variable? Variable, because flux proportional to IA. Whenever load on motor changes, current drawn by motor changes. Whenever current changes, definitely flux also changes. So the flux of series motor is variable. The flux of series motor is variable and which is proportional to the armature current always. This is main flux. Armature flux anyhow depends on armature current only. But in series motor, main flux also depends on current IA. First one, speed versus IA. Speed versus IA. First of all, speed is inversely proportional to, that is V minus IARA. EB by 5. EB means V minus IARA plus RSA. Speed is proportional to EB by 5. V minus IA into RA plus RSA divided by 5. And this flux is proportional to IA only. Now in this equation, speed proportional to, we need speed versus IA. Numerator there is IA, denominator also there is IA. So which IA is dominating? Numerator one or denominator one? Which IA is dominating? Denominator IA is dominating. Why? Because this is a drop, it is resistance drop. Resistance drop is very less because armature resistance is low value and series resistance also low value. Both are low resistance. Generally shunt field resistance is high value, but series resistance is what? Low, less than 1 ohm mostly. That's why it is a negligible drop. It is negligible. So if we neglect this drop, then mainly speed is inversely proportional to current IA. Now using this relation, whenever IA is 0, what is the speed of motor? When IA is 0, speed is infinite, means dangerous high speed it is. The series motors under no load rotates at dangerous high speed. So remember, under no load condition, the speed of series motor is dangerous high speed. have you operated any time in your lab series motor under no load condition? We never operate because the lab people will not allow to run the motor at no load first because they know dangerous speed. So you should observe or not? Yes, we should know practically how it is rotating or not. Yes, it rotates at dangerous high speed. Now what is the problem if it rotates at dangerous high speed? What happens in the motor? At dangerous high speed operation, centrifugal forces in motor is very, very high. Centrifugal forces are very high. Now what this centrifugal force will do? Centrifugal means The force is acting out towards the center of the body. Because of that heavy centrifugal force, mainly commutator and brush, that assembly will damage. Commutator also rotating at high speed, same speed, na commutator speed also. Then the brushes, whatever we place, the friction developed is very high. The brushes gets damaged first. Brushes will damage due to high temperature. Commutator also may damage. At the same time, whatever the winding is there in the rotor, there are winding here, open slots, winding. Because of centrifugal forces, what happened? Whatever winding is there inside the armature, these windings will come outside. Whatever the coils you placed, all will come outside. That is the centrifugal force, very high centrifugal force. That means your total machine will damage, motor will damage. So we should never operate any motor at dangerous high speed. See, you can observe dangerous high speed also in your home in mixers. In the mixer, how? So in the mixer, don't place any jar in the mixer. You just, without any jar, any load on that, you try to switch on the mixer. Then what is the speed it runs? Check it is once. Very high speed it runs. That is only series motor. That is also series motor, but AC supply we give. Same as it is in DC also. It rotates at dangerous high speed. But is it any problem in mixer if you operate? No problem. Why? Because they are small rating. Small rating, and we design completely compact. That's why the winding or commutator nothing will damage, even if it rotates at high speed. That means that you should not run that motor or mixer for a long time like that. Then definitely that one also will damage. Mainly brushes will get wear and tear. That's why we should never operate under no load condition. Series motor speed is dangerous high speed. See, under no load speed is very high, but whenever load increase, IA increase. Whenever load increase, IA increase. When IA increase, speed decrease. How the shape it is? It will decrease like this. Is it correct? Linearly it won't decrease, because actual numerator also there is a variation of IA. That's why it will decrease non-linearly like a rectangular hyperbola. See the figure. So like this it will reduce like a rectangular hyperbola approximately. Like rectangular hyperbola like this. See here, there is one important observation in this. It is decreasing. Whenever current increasing, speed decreasing like a rectangular hyperbola. And here, observe. Whenever IA increase, what is the flux in series motor? Also increase. Flux means main flux it is. Flux also increasing. Whenever main flux increase at one of the current, the flux will reach maximum value and then it saturates or not? Yes. Now it saturates. Whenever it saturates, flux is constant. If flux is constant, then what is the speed? Also constant. Speed inversely proportional to flux. That flux proportional to IA. When IA increases, flux increase, speed decrease. Speed decreases. So, observe here. Let us assume at this particular value of current IA, the flux reaches constant, saturation takes place. After that, the speed of motor is almost constant. So little big diagram you take it is, because now observe. This is saturation point. After saturation, actually the speed, if you neglect that resistance drop, the speed of motor is constant. This is. Speed is constant because flux reaches constant. All of you understanding or sleeping? No response. All of you listening, no? Okay, good. Okay, see. At a particular value of current, as flux reaches maximum, it saturates. Then the speed of motor is almost constant. This is the saturation point. So after saturation of field poles, the speed is almost constant speed. Suppose saturation neglected, negligible. Suppose sometimes they give this statement, saturation is neglected. Then what is the shape of speed versus IA? Whenever saturation is neglected, whenever IA increase, the speed decreases or not? Yes, this is IA. If saturation is neglected, the speed of motor in the same shape continuously it reduce zero. And wherever that speed is zero, that condition we call stalling condition of motor. Stalling. That is called stalling condition. See, just in your lab, you apply brake on the motor. Brake test. We will tight the belt now. Apply the brake or load applied. Like that, apply the brake on motor, load on motor continuously up to it stops. Now, wherever it stops, then the current is very high at that time. That is called like a blocked rotor. Already you know induction motor, blocked rotor means short circuit condition. Then current is very high. So that is called stalling condition of motor. What is the stalling condition? If load on motor is increases up to, if load on motor is increases up to, the speed of motor becomes zero. That condition we call stalling condition of motor. Stalling, starting, that almost both are same. Starting condition or stalling condition, both almost same, because stalling means speed zero. At the time of just starting, what is the speed of motor? Zero on. That's why armature current drawn by motor is very high. That what is that current equation? IA equals to V minus 0 by RA plus RSC if it is series motor. This is very high current at the time of starting. Stalling condition also same, speed zero. Okay, so this is the dotted line. The speed of motor is constant with saturation. This is with saturation. If saturation is neglected, this is without saturation. If you neglect the saturation, the speed versus IA continuously you will get like rectangular hyperbola and become zero. With saturation, after a particular load, the speed reaches constant. Speed will not change after that. Okay. So there is one question previously in engineering services like this. They given one graph, speed versus IA of a series motor. And here at this point, they said saturation takes place at a particular value of this IA, there is saturation. Due to that saturation, what is the speed of motor? What is the speed of motor after saturation? Like this is A, B, C, let it is D. So they will give, this is the saturation point. They given that this is saturation point. Now after saturation, what is the speed of motor? Which curve represents speed of motor? Which curve represents speed of motor? A, B, C, D. Which curve represents speed of motor after saturation? Yes, after saturation, B only, because what is the speed of motor after saturation? Almost constant. The B will represent that. Okay, speed of motor is constant, but here if you observe, I did not draw it is exactly constant. It is having some slight decrease in the speed. This is the exact variation. It is not exactly constant. Constant means like this. This is, but I drawn little slight variation in the speed after that. Slightly speed decreases. Slightly speed decrease. What is the reason for that? This drop in the speed here is due to armature resistance drop. Previously we neglected that. That's why we taken constant speed. If you neglect the armature resistance, speed is constant. But if you consider this drop, whenever IA increase, drop increase, slightly speed decrease. Okay. This curve B represents after saturation. Clear all of you this point? Okay. See, in the previous graph here, I said speed is constant because we neglected this drop there. If you neglect this, speed inversely proportional to IA. Whenever IA increasing, whenever flux reaches maximum and saturated, then no variation, speed constant I take. But if you consider this drop after saturation, I will write here. After saturation, what is the speed exactly? Flux is constant. Flux will not change. Flux is constant. Now, what is this variation? V minus IA into RA plus RS. Now, if you consider this drop here, whenever IA increase, this drop increase, then what is V minus this drop? Slightly decrease. Speed of motor slightly decrease because small drop it is. That's why this variation is there. Okay. This black line is what? Constant. When it is constant, if you neglect this drop. Clear now? Okay. This is the first one, speed versus IA. Speed versus torque also same. So I don't draw again the same characteristics. Speed IA, speed torque, both are same. Okay. Speed torque also same. Now let's see the second one, torque versus IA. This is important. Torque versus IA characteristics. Torque is proportional to product of flux and armature current. Now, in case of series motor, torque is proportional to IA, flux is proportional to IA, IA into IA square. Since flux proportional to IA in series motor, because of that reason, torque is proportional to IA square. Now, what is the variation? Whenever IA is 0, torque also 0. Whenever IA increase, how torque increase? Like a square of current, means increase in torque is very high because of square it is. That's why, what is the variation? Y square equal to 4ax form it is, like a parabola shape. The torque of motor increase whenever IA increase, the torque increases like a parabola. But is it always like a parabola up to infinite? No. Up to a particular value of current, let rated current, up to that parabola shape. But at this current, assume that at this value of current, saturation of poles. Flux proportional to IA, no? When IA increase, flux also increase, poles will saturate at one current. Once there is a saturation, this is before saturation. Before saturation it is this condition. But after saturation, flux will not change further, then torque is proportional to only IA. Torque is proportional to only IA. Flux will not change. Now what is the relation here? From this point, whenever IA increase, torque also linearly increase. Therefore, if IA increase from here, torque linearly increase. This is torque proportional to IA. And this is torque proportional to square of current IA square. What is the shape of this parabola? This characteristics important. What is the shape of torque versus IA before saturation? Before saturation is parabola. After saturation is straight line. After saturation is straight line. Okay. So important is The series motor is having highest starting torque. Highest starting torque. Because in case of shunt motor, what is the torque relation? In shunt motor, torque proportional to only Ia because flux always constant there. If Ia increase, torque also increase little bit. But in series motor, if Ia increase, torque increases by so much. Suppose torque is current is 2 amperes. What is the torque in shunt motor? Related to torque proportional to 2 only. But in case of series motor, what is the torque proportional to 4? Means torque increment is very high. Therefore, what is the application of series motor? Tell me now. Applications of series motor. This series motor is having highest starting torque. Because of that reason, this motor is suitable for the loads which required a high starting torque. So which requires high starting torque? Traction or train. A train required very high starting torque because it is a heavy body, high inertia it is. Because of that, it requires a high starting torque at the time of starting. Therefore, for that reason, series motor is suitable for traction. Not only traction or lift. Which lift? Not the lift whatever we are using right now in the buildings. Not that lift. Lift in the sense I'm saying lifting. If you go to construction site, we have hoists, construction site, or cranes. Okay, this type of whatever that lifting applications we use, hoist, cranes, and all. So these are all lifting, means heavy materials they are lifting. So for that lifting, they need a series motor there. Yes, right now we are using also in the construction site series motor. But which series motor? AC series motor, that is. Not DC. AC series motors we are using in that places. In all these cranes and hoists and all. Okay, so write the applications clearly. Right here. And first of all, what is the speed of series motor? No load to full load. No load to full load. The speed of series motor continuously decrease. No load is dangerous high speed. But full load is dangerous high speed means let 5000 RPM. This is no load condition. Now under full load, what is the speed of motor? Normal, 1200, 1300, 1400 like that. That is the full load speed. What is the variation? No load is 5000, full load is 1200. How much variation? Nearly 3000, 4000 variation. So this much variation we call variable speed motor. This is a variable speed motor. But what is the speed of shunt motor? Almost constant. Because if no load speed is 1400, full load speed will be 1350. 50 RPM change. That is not the big variation of speed. So series motor is treated as variable speed. Write one point. From no load to full load. From no load to full load. The speed of series motor. The speed of series motor is variable. Is variable. Hence, it is treated as a variable speed motor. A variable speed motor. Full stop. Make a note. Right. Under no load, this motor rotates at dangerous high speed. This motor rotates at dangerous high speed. Also, it is having very high starting torque. Very high starting torque. Hence, it is suitable for the loads. It is suitable for the loads which requires which requires a high starting torque, and which are permanently connected, which are permanently connected, which are permanently connected. Now, what is the example for this? Permanently connected traction. If you take trains, the engine itself load on the motor. Whatever the engine body is there, iron body, that is itself load on the motor. So whenever motor starts, there is a load on that. Okay, that is like permanently connected load on that. And lifting application also. When we will lift the material, if there is load on that. So at the same time, there is some load. Means no load speed actually dangerous. That is we avoided because permanently load are connected. The examples are applications or in the traction we use traction, and we can use it is in lift in the sense cranes, hoist, etc. So for the loads which are permanently connected and which requires high starting torque, there only we use series motors. But right now we are not using series motors in traction. But this is a application of series motor having high starting torque suitable for traction. It is. Remember these points. Hoist is lifting. So I think everyone has seen in the construction of buildings, apartments or any commercial buildings. So there we have heavy lifting cranes or hoist, we call that is to lift the materials. There we use. Oh yes. Response is very slow now. I think everyone is just listening with saturation condition. So all of you there, just raise the hand once. Okay, very good. Okay, enough. Okay. So just wait one more compound motor characteristics. After that, we will see some introduction of speed control. Then we stop for today. Okay. Now one more is compound motor characteristics. Right now, compound motor characteristics. Compound motor characteristics. So both cumulative and differential in the same graph we will draw speed versus IA. Speed versus IA. What is the speed of compound motor under no load condition? No load means current zero. At that time, what is the speed of these compound motors? Rated speed or dangerous high speeds? Normal speeds only, rated speeds only, not dangerous high speed. Only series motor no load speed is dangerous. Remaining all motors will rotate some constant speed, nearly rated speeds only. Okay, so at no load, let this is the speed of both cumulative and differential. For both, same speed I am taking. Now, if it is cumulative, how the speed will change? If it is differential, how the speed will change? N proportional to EB by phi. And what is the total flux in compound motor? Phi SH plus or minus phi SH. If it is cumulative, take plus. Plus for cumulative, minus for differential. Okay. Now let us take cumulative first. Speed is inversely proportional to phi SH plus phi SH. So neglecting that small variation in back EMF, V minus IARA, that armature resistance drop neglecting, that's why directly I have taken field here. Now, whenever load increase or current increase, out of these two fields, which field increases? So already you have seen so many figures. Whenever IA increase, mainly series flux increase. Shunt is almost constant. Then phi SH plus phi SC. What is the overall flux increase? Speed of motor decrease. So in case of cumulative compound, if IA increase, the speed of motor decrease. This is for cumulative compound. This is for cumulative. So it is almost like shunt motor. Speed decreases if load increases. Cumulative compound motor. Now for differential compound, speed inversely proportional to phi SH minus phi SC. Now whenever IA increase, what is the series flux? Increase. Then what is overall flux now? Decrease. Then what is the speed? Increases. So if IA increase, the speed of differential compound motor increase. This is for differential compound motor. This is the dangerous motor. Dangerous it is. How dangerous? Suppose if this motor we use in the giant wheels, definitely it never stops. It will damage the load. What is the load? Suppose in the giant wheel there are total 20 seats. 20 persons are seated. Load is very high. Then differential compound generator speed continuously increases. If load increase, speed continuously increase. That is a dangerous motor. Why? Because this is the only motor having this type of characteristics. So practically tell me now, generally, if load on any motor increase, what is the speed of motor? Shunt motor, separately excited or induction motor, any motor. If load increase, what is the speed of motor? Decreases. That is a motor nature, every motor. But there is only one motor reverse, this one, differential compound. What is that? If load increase, speed also increases. See how much dangerous it is. See, load is safe. Whenever load magnitude increase, whenever its speed decrease, load will be safe. But now, whenever load increases, speed also increases. So this is the dangerous motor. So this type of motor, we don't have any applications. So we never use differential compound motors. Okay. And cumulative compound motor we use. Just like shunt motor it is. See, almost speed slightly decreases whenever current or load increases. Speed torque characteristics also same as it is this. So I'm not drawing again torque proportional to phi SH plus or minus phi SC into IA. Same variations you get for speed torque also. Okay. Now let's see. Second one, torque versus IA characteristics. Second, torque versus IA. Torque versus IA. If it is cumulative, the total flux is addition phi SH plus phi SC into IA. If it is differential, the total flux is difference phi SH minus phi SC into IA. Now, first cumulative, let us take cumulative phi SH plus phi SC into IA. Whenever current IA increase, series flux increase, overall flux also increase, and overall torque also increase. It is just like current increasing, flux also increasing proportionally. It is almost like square of previously we have seen series motor, square of the current. It is also almost like that. That's why whenever IA increase, the torque of cumulative compound motor also increase like a rectangle, like a parabola shape, just like series motor it is, like a parabola shape. Torque increases like a parabola shape, and at a particular current, again the total flux will reach maximum saturation of poles. Then torque is constant, just like series motor characteristics you get. Just like series motor, parabola before saturation, straight line after saturation. This is for cumulative compound. Okay. Next, differential compound. How we get for differential? Check it is. Differential means 5SH minus 5SC into IA. Whenever IA increase, series flux increase, overall flux decrease, because difference it is. When IA increase, series flux increasing, overall flux decreasing. Then current increases, flux decreases. What is the resultant torque? Is it same? No, because effect of current is main here. Current increasing means torque increases, but not like cumulative compound. Cumulative compound more increase in torque because both increases, but here torque slightly increase. So that's why you get for differential compound, the characteristics you get like this. This is for differential compound motor. Okay. The torque in differential is less than cumulative compound. There is no any particular shape for that because both are changing here. That's why approximately we can draw like this. That's it. Now, one important question here. Cumulative compound motor. Cumulative compound motor. It is having the characteristics sum of shunt motor characteristics plus series motor characteristics. This is the sum of the two motors. Why? Shunt motor. What is the speed torque characteristics of shunt motor? Whenever torque increase, speed slightly decrease. That is only it is having here. See, whenever torque increase, the speed slightly decrease, just like shunt motor. And series motor characteristics are what? Torque versus IA. The shape of series motor is parabola before saturation, straight line after saturation. It is similar to series motor. So it is having the combined characteristics of both shunt and series. It is having combined characteristics. Combined characteristics. Okay. That's why it is suitable for the loads like which requires constant speed and which requires high starting torque. Like what is the application of that cumulative is? We can go with paper mills, a printing machine, that is mainly printing machines. Printing machines or drilling machines. In some of the drilling machines also we use in large size, and also uh, like rolling mills. Rolling mills. So there we required in some of the rolling mills for crushers like that high starting torque because of heavy loads we use in crushers. So there in the rolling mills we use cumulative compound motors. Okay, just some examples. But practically we are not using this compound motor. DC motor applications are very less practically. Which motor is mostly we are using in DC motors? Series motor, universal motor, that is in many places we are using universal motor. Okay. So this is about characteristics of motors. So why we are using three-phase induction motor nowadays? Because of controllable it is now, because drives we are using power electronic drives. So using that whatever we want we can bring. If you want high starting torque you can bring, you can get it. Or if you want high speed you can get high speed. That is easy because induction motor cost is less compared to series motor of same capacity. Induction motor cost is less, maintenance also less. That's why induction motors are best one, durable, that is simply. Okay. Okay, so with these characteristics over, the next important one, speed control methods. It's studying speed control of DC motors. speed control of DC motors. See, this is an important topic not only for written point of view, written test point of view. For every interviews, speed control methods are very important. That means not only for DC motors, induction motors also we have speed control. So that is also important. Compared to DC motor speed control, induction motor speed control is very, very important in the interviews, because most of the students, what they are doing mistake is they are neglecting, they are writing examinations well, but once they attend interviews, then they are realizing what we are learning. Up to that, nobody knows anything. In the interviews are major role now, because PSUs taking you directly from gate. Maybe you got a good gate rank, they need to test whatever they required or not. Yes, now they are testing mainly in the interviews, technical interviews. So in that interview, if you don't perform well, if you got top 100 rank also, no use. That's why at least try to learn some subjects like machines. Particularly, you need some practical information. Without that, you cannot understand what is happening in actual practically. Theoretically different. Theoretically, some equations, some topics or some statements will satisfy, but practically they don't satisfy. Just like I said previously, in a DC shunt motor, if field winding is open, what is the speed of motor? Dangerous high speed. That is theoretically. But practically, motor comes to stop. And both are exactly opposite or not? Yes. Then how it is? That's why you should know some practical information also. Okay. First tell me advantages. What is the advantages of speed control for any motor? That is not only DC motor, for any motor, what are the advantages? What is the need to control the speed? Well, advantages are what? The first and foremost thing is in your home, ceiling fan. Ceiling fan. That fan is operating with speed control or without speed control? Tell me. Yes, almost 99% there will be a regulator to that. Without that, we are not comfortable first. Ceiling fan regulators. That is a speed control method. Now, everywhere we are controlling the speed of motor. See, if there is a motor, suppose you bought a motor, you buy a motor. Now, the motor has to run as it wish, or the motor has to run as we wish. How it has to run? As we wish. However we want, like that the motor has to rotate. If motor is rotating as it wish, we don't want that type of motor, we will throw it away. We want to rotate the motor, or we want to operate the motor at our desired conditions. At our desired conditions. Suppose the best example for the speed control is lift. Lift in the apartments or any commercial buildings, everywhere. How the lift is operating, tell me? With speed control or without speed control? With speed control. How it is operating? Slowly it starts and slowly it stops whenever it is stopping. Now there are some lifts will be there in some of the buildings. You cannot identify that when it starts, when it stops. That much smooth operation of speed control will be there. But there are some lifts you can easily identify. Now lift started, now lift stops. And how it is operating? Suppose assume no speed control. Now once you entered into the lift, you have to wait. You need to think about the lift only there when it starts, because no speed control. Now, for example, suddenly it starts and suddenly it stops. Then is it comfortable for loads? No. Load means we only load in that. So we are not comfortable. So comfortable means the lift has to start slowly and pick up the speed and then stops again slowly. Like that it has to operate. That is with speed control. Not only here. If you visit any manufacturing industries, any manufacturing, food manufacturing or steel manufacturing or paper or anything, that is, everywhere there is a speed control. Because if you see on the belt conveyors, everything will move. Manufacturing anything, that is steels or any paper mills, or any food manufacturing industries, anywhere processing industries and all, the products will move on the belt or in the uh, steel plates or steel blades slowly at constant speed or variable speed. So we need to control the speed of everything there. Speed control is nowadays very, very important. If you go to MTech also, there is no again separately machines, advanced machines are like that. It is not there. Only we have power electronic drives, one subject in MTech. That is there we will learn completely about drives. Drive. Okay. First, see what are the advantages. Right. First advantage. It is possible to operate the loads. It is possible to operate the loads at any desired speed. At any desired speed. We can operate at any desired speed, whatever we want. At any desired speed. Second, it is the loads are well protected. The loads are well protected with speed control. The loads are well protected with speed control. Okay, loads are well protected means you take anything. When there is a speed control, you can protect the load. Best example, lift only I said. In the lift, the whatever the person is entered, they are well protected. Slowly it starts, slowly it stops. Otherwise, they are not protected. Suddenly it starts, suddenly it stops. So with that, loads will damage. So with speed control, the loads are protected well. Next, third advantage. When there is a speed control, it is possible to increase the life of motors also. Suppose you take a ceiling fan in your home. For one fan, there is a regulator. For other fan, there is no regulator. Assume that. Now operate one fan with regulator at low speed. Operate other fan which is not having any regulator at high speed, because if there is no regulator, when you switch on, what is the speed fan will rotate? High speed, only one speed. Now operate one fan at high speed, other fan at low speed with regulator. Now let us allow the fan up to their die. Now which fan will definitely die first, or which fan will damage first? Lifetime of the fan which rotating at high speed will reduce first, because at high speed of the every motor, bearings will damage first. Bearings, because of continuous friction in that, bearings will heat it up. Finally, bearings will damage inside. And like that, the life of motors will reduce. But if the fan operating at low speed, the life of the motor you can increase. That is one advantage of speed control. That is the life of motors can be increased. Can be increased. Okay, so these are some advantages of speed control. So not tomorrow, mostly by Saturday, if possible, we complete. Otherwise, Sunday also some time is required to complete. Okay, Saturday also we will have class. Yes, exactly. Okay. Now, before going to speed control methods, let's see the types of drives we have. Types of drives. First, tell what is a motor, what is a drive. What is difference between motor and drive? Motor is what? Drive is what? Motor is nothing but suppose take a DC motor or take a ceiling fan in your home. That ceiling fan in your home is a motor or drive? The ceiling fan in your home is a motor or drive. For that, you need to check in your home there is a regulator or not. If there is a regulator, that fan is a drive because you are driving at any speed. But motor means it rotates only at one constant speed, no speed control in this. Drive is nothing but a motor with speed control. Motor with speed control. Okay. Motor with speed control, that is a drive. Now, how many types of drives we have? So I think already you know about the drives. In induction motor also it will come. Yes, very good. Drive is nothing but machine plus power electronics plus control system. Yes, that is only correct. Very good. Okay. So we have closed loop speed controls. Speed control we use with closed loop speed control for effective operation of the motors. Now, there are three types of drive mainly we have. One is constant power drive, constant power drive. Second, constant speed drive, constant speed drive. Third, adjustable speed drives, adjustable speed drive. Three types of drives we have: constant power drive, constant speed drive, adjustable speed drive. So let's see what is this one by one. First, constant power drive. First one, constant power drive. Constant power means power must be constant. That's it. Power. What is the power equation? Torque omega. What is torque omega? 2 pi n by 60. So power is nothing but 2 pi nt by 60. This must be constant. Power must be constant in motor. So in order to get constant power, anyhow 2 pi constant, 60 constant always. Now power proportional to nt. Power constant means the product of nt must be constant. From here, the speed is inversely proportional to torque. Now, which motor is having this type of characteristics? Speed inversely proportional to torque. Which motor has these characteristics? Yes. Speed torque characteristics of series motor is inversely related like this. That is only, no, when torque increase, speed decrease. Torque increase, speed decrease. Which motor having these characteristics? Series motor, rectangular hyperbola. Series motor is suitable as a constant power drive. Series motor is suitable as constant power drive. Without any control also, series motor self behaves as constant power drive. Because of its characteristics it is. Speed torque is inversely related. Whenever torque increase, speed of motor decrease. Okay. Constant power drive, nothing but speed torque characteristics, because in questions examinations you will get under constant power drive what is the variation of speed with increase in torque. If torque increases, speed decreases, inversely related. Okay, next. Next, second one. Constant speed drive. Tell me which motor is having this type of application. Constant speed drive. Which motor will give constant speed? Which motor will give constant speed? Means the speed torque characteristics are constant. Speed is constant irrespective of torque. Speed is constant. Even torque increasing, speed is almost constant. Which motors is having this type of characteristics? Almost speed is constant. Shunt motor, separately excited motor, cumulative compound motor. So these motors are having this type of characteristics. Speed is almost constant. If you neglect that small drop, almost constant. Okay, induction motor also comes under this. Induction motor, constant speed drive it is. So this is constant speed drive, but mainly we have to know about adjustable. That is important for us. Right. Next, third, adjustable speed drives. Adjustable speed drives. I think this one you will get in induction motor also. Adjustable means this is the graph of adjustable speed. We can adjust the speed below rated, above rated. That is the speed control it is. We can change the speed of motor. Let it is rated speed. This is below rated speed. This is above rated speed. The speed of motor adjustable. Below rated, above rated. Below rated, the torque is constant. Above rated, the torque is variable. Above rated, the torque is variable like a rectangular hyperbola. Next, power. Below rated, power is linearly variable. Above rated, power is constant. Above rated, power is constant. How we get this proof? So did you observe this type of graph anywhere previously? Have you seen this type of graph previously? Tell me. Have you seen anywhere this type of graph previously? Synchronous motor. Any other way? Yes, in induction motor also it will come. Okay. So the proof of this graph, so we will see in the speed control methods. Speed control methods. So there we will see the proof of this. How we are getting below rated, torque is constant, power is variable. Above rated, power is constant, torque is variable. So this proof I will show you in the speed control methods, how we get. Okay. Now, right side heading, speed control methods. See, the questions on this graph is very, very, very important. Not only for DC motor, for induction motor also. Like previously in many examinations, direct questions are constant power drive is suitable for which of the following speed control methods? Constant power drive is suitable for which of the following speed control methods? Means constant power drive above rated speed. Where we have constant power above rated speed. Now above rated speed, which methods are suitable? So in DC motors, there are 3 methods total. Easily you can remember that. But problem is with induction motor. So first write speed control methods. Speed control methods. Speed control methods. The speed equation is n proportional to EB by 5. What is EB? V minus Ia Ra by 5. Now, in order to change the speed of DC motor, what we can change here? Voltage you can change. Armature resistance means externally you can add some resistance, that is called armature resistance control, and flux control method. Only 3 methods available for us to control the speed of motor. That's why it is difficult to control the speed of DC motors. But induction motor you can control like anything. That much easiness is there for induction motor. Why it is, I will show. See here first. The speed of DC motors can be controlled by first flux control method. Second one, armature resistance control. Armature resistance control. Third one, voltage control method. Voltage control method. See, out of these 3 methods, flux control is suitable for high speeds, above rated speeds, and remaining 2 methods is suitable for below rated speed. So easily you can remember this. Flux control above rated, armature resistance control, and voltage control below rated speeds. Easily. Now you can apply here. Below rated speed. Below rated speed, armature resistance control, and one more is voltage control. These two suitable for below rated speed, and above rated, flux control. This is very easy to answer. So under constant power drive, which method suitable for DC motor? Flux control. Under variable power drive, which method suitable for DC motors? These two methods. Like that, you will get the questions. But what is the advantage of induction motors is, in induction motor, you can control the speed from stator side. You can control the speed from rotor side. Any side. Stator side you can control, rotor side also you can control. Stator side means what? Stator supply voltage you can change. Supply frequency you can change. Pole changing also available. So these are all from stator side. And rotor side means what? Rotor resistance control. Rotor EMF injecting control. These are all from rotor side. And cascading of induction motors. This is also from rotor side. Cascading of 2 induction motors. Like that, you can control the induction motor speed anywhere. That is stator side control, rotor side control. And again, the total methods in induction motor are voltage control and frequency control. In the frequency control, again, there are 2 methods: pure frequency control and variable voltage, variable frequency control. That is called V by F control. And after that, pole changing technique. Pole changing. And after that, rotor resistance control. After that, EMF injecting. EMF injecting, again, 2 methods. One is in phase injecting and out of phase injecting. And after that, cascading of 2 induction motors. In cascading of 2 induction motors, 2 methods: cumulative cascading, differential cascading. So like that, there are number of methods, numerous methods available to control the speed. But DC motors, how many methods? Only 3. That is the drawback of DC motor. That's why mostly some of you asking why we are using induction motors, because these are the advantages of induction motor. Like that, we can control the speed like anything in induction motor. Very easy to control, but very difficult to control DC motor speeds. Okay. And you need to remember in these methods, which method for above rated, which method for below rated. So little difficult, it is not difficult. If you learn, you can easily remember that. Okay. Same adjustable speed drives applicable for induction motor also it is. Okay. Okay. So anyhow, So tomorrow we start this one by one, three methods: flux control, armature resistance control, voltage control. So today I stop here. This is enough. Tomorrow, same timing. Okay. Yes, speed inversely proportional to torque means that is series motor only that nature. Okay. So to all of you, happy Durga Puja. Yes, tomorrow festival. That's why we have full class. Okay. So don't worry. By tomorrow, almost we take only one break, and as much as possible around 7:30 will be. Okay. So I am from AP. See, no need to remember characteristics. Learn and forget. That is my concept. Learn and forget everything. So don't be stressed with your mind. Just learn and forget everything. Be cool. Okay. So enough. I cannot see your messages also now because there are more than 1,000 messages. So I cannot scroll it is also. Okay. So anyhow, tomorrow we meet again. Okay. So I'm leaving today. So tomorrow we see if any doubts also. Okay. Good night.